Hi everyone, welcome to Vedantu NEET English. I'm Diksha Kaushal, your chemistry master teacher. So guys, everybody in the chat box, am I visible? Am I audible to you or not? So today is going to be our not last class, but we have completed the syllabus. We have done physical, organic, inorganic chemistry. We are going to complete today itself, right? The last topic, that is group number 17, 18 and some of the parts of group number 16 are left. So we are going to complete that today itself. But now students are asking that, ma'am, I was seeing your comments. So many students are actually confused that whether P block is in their syllabus or not. If it is in the syllabus, then is it only the trends or the preparation and the properties are also in the syllabus? So to clarify that thing, see, firstly, you don't have the syllabus of NEET 2025, right? Okay, so they have not published the official syllabus here, right? So last year it was published at around, I think, in the start of October, I think maybe 3rd or 4th, maybe 6th October, I guess, right? So in that time they have published the syllabus last year, 2024, right? So now they have not published any syllabus, and last time also there were not very big changes, right? It was not something in chemistry, something was not added, right? Only the topics, they have deleted some topics in chemistry. So as far chemistry is concerned, I'll tell you that most probably they are not going to add something new here, right? And also they will not, most probably the syllabus is going to be the same only, right? And if you talk about, ma'am, P block, see, P block is a very, very important chapter. I know it is not in your new NCERT. So that's why students get even more confused that it is not in the new NCERT, that, ma'am, how come you are teaching us this chapter, right? Because last year it was in the syllabus. So most probably like 99.99999% it is going to be in your syllabus this year also, right? Otherwise they should have told us like 1-2 months before only. That's why I took my time. I told you that I'll wait for the syllabus. By the end of November, I'll see if they give us any syllabus. But still, there is no, like, we can't see any syllabus, nothing official regarding that, right? So, yes. But now, you don't need to like worry about that thing, whether trends are in the syllabus, whether properties and preparation are in the syllabus. See, I'll tell you last few years trends, right? So basically, definitely they are going to ask you questions from the trends, the exceptions that I told you yesterday of each group, right? The thermal stability, reducing power, bond dissociation energy, ionization energy, electron gain enthalpy, radius, size, like all of these trends, the exceptional trends especially, you need to know. Second thing is, if you are talking about the preparation and the properties, that's why yesterday I did that preparation and properties really, really fast, right? What was the reason? Some of the things I told you that this is not important for you, you can skip that. What is the reason behind that? I don't want you to skip as it is, that I don't want to do I don't want to understand any compound, like, don't do the preparation, but do some of the properties, right? They might ask you. That's why I have picked up NCERT. I am teaching you line by line so that you can know what are the topics that you can skip, what are the reactions that you can skip, and what are the reactions that they can ask you, because they also relate to the other chapters, right? Because P block is related to somewhat chemical bonding also. In chemical bonding, you have structures, right? Okay, so structures you need to know. All the structures that are mentioned in your P block, you need to know that, right? Whether they are talking about any other compound or simple structures. That's why oxoacid structures are also very important for you, right? Okay, understood. I hope this thing is now clear to you, and for this I want you guys to like this session, right? Because your ma'am is taking the session on Sunday as well, right? Because I know you guys are like free on Sunday, so let's take a session on Sunday, right? Okay, so everybody, yes, now is there any confusion regarding P block, whether it's important for you or not? Yes, everybody. P block is a very, very, ma'am, wear specs, ma'am. Yes, just give me a second. I sometimes forget. These kids are like, ma'am, don't stress your eyes. Ma'am, you look pretty in specs as well, okay? You just tell me this thing, ma'am, you look pretty in specs as well. Be confident wearing specs. Okay, so now I am into that padhaku zone, right? So, okay, yes, everybody, shall we start? Okay. So yesterday we did group number 16. Today also we are going to do group number 16, right? But some of the portion of group number 16 was left. We are going to do that portion, right? So let us start with that portion. So we were at this particular page of your NCERT, right? Even if you don't open your NCERT, because I think if you have new NCERT, so that is not there in new NCERT. That is there in, you can pick out some PDF from the net, right? From there you can understand, and you can take the prints of that chapter, right? Okay, yes. Now, let us see, we were at group number 16. All the orders, the reactivity orders, they are important for you. So, let us see reactivity with oxygen. So, all these elements form oxides, right? They definitely form oxides, right, with oxygen, right? So, when we talk about group number 16, it was basically this, NS2NP4, that was group number 16, right? Okay. So when they are forming the oxides, they are forming EO2 and EO3 type of oxide. These kind of oxides they are forming. These kinds of oxides they are forming, right? So let us take the example that what if it is having plus 6 oxidation state or plus 4 oxidation state. If it is having plus 6 oxidation state and this is having minus 2, if it is having plus 4 oxidation state, it is having minus 2, it will become E2O6, that will be EO3. It will become cross multiply E2O4, that will be EO2. That means these are the two oxides that it can form having the oxidation state plus 6 and plus 4. So you don't need to cram all these things, right? So very simply you can say that EO2 and EO3 type of oxides are formed here, right? So ozone. Now let us see. Ozone means when oxygen combines with two other molecules, you can say two other atoms of oxygen, right? It forms O3, that is O3, that is also called ozone. Now ozone is very important compound, right? Ozone and sulfur dioxide, that is also important compound, right, are gases, while others are not gases. Selenium dioxide is a solid. Reducing property of dioxide decreases from, now this is important and this has also been asked, that the reducing property, which property? Reducing property of dioxide decreases from SO2 to TeO2, right? So it will decrease, right? From SO2, from sulfur to beryllium, it will decrease here. SO2 is reducing while TeO2 is oxidizing in nature, right? SO2 is reducing in nature and TeO2 is oxidizing. Besides EO2 type, sulfur, selenium and beryllium also form EO3. You have seen SO3 oxide, right? SCO3 and TeO3, both type of oxides are acidic in nature, right? So basically the important thing to note down is the oxidizing and reducing nature that they have mentioned here, that SO2 is reducing and TeO2 is oxidizing in nature. That you need to understand, right? Okay, so that is the important point that I have underlined here. Next thing is reactivity towards the halogens, right? So if you talk about the same thing regarding halogens, right? If you talk about the same thing regarding halogens, we know one thing for halogens. What we know? For halogens, we know one thing. Don't do this, bro. Don't ruin my lecture, buddy. Okay, so now this is plus 6, right? And this is plus 4, right? So again, it is with X negative, that is halogen. So with halogen, what will happen? This is E plus 6 X negative, it will become EX6. And here it will be E4 positive X negative, it will be EX4. So these two kinds of hydrides, halides will be formed, right? Halogen, no, so it will be halides will be formed here. So, right, so what are the halides that are formed here? Form a large number of halides type EX6, EX4. These two though we have seen, where E is having oxidation state plus 6 and here it is having plus 4. Now, plus 2 halide, right? Like SCl2, SF2, right? So these are very rare, but they are found, right? They are also found here, which is having E, that element is having plus 2 oxidation state, where E is an element of the group, X is the halogen. The stability of the halides, now this is very important, right? When we will talk about halides, right, only simple halides, halogens in group number 17, all the trends of group number 17 are also very important, right? The stability of the halides decreases in this order. They are saying if we talk about the stability of the halides, right, that will decrease down the group, right? Amongst, if you talk about amongst hexahalides, hexafluorides are only stable halides. Now this question has also been asked, that amongst, if you talk about hexahalides of group number 16, only hexafluorides are stable. Okay, hexafluorides are stable. That's why you have seen SF6, right? SF6, that is a stable molecule that we talk about in chemical bonding, right? Are the only stable halides. All hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride, that is SF6, is exceptionally stable for the steric reason, and the structure here is important. The hybridization of SF6, all the things about FS6 is important, and this we have done, this we have studied in chemical bonding, right? Now next is okay, amongst tetrafluoride, now they are talking about tetrafluorides, right? Hexafluoride we have discussed that only hexafluorides are stable, other hexahalides are not stable, right? So let us talk about tetra, where you have 4 fluorine atoms. The let us say SF4 is a gas. Now SCF4 is a liquid, but TEF4 is a solid, because now S, TE and SC, these three will form the tetrafluorides. Out of this is a very, very important gas. Then with selenium it is a liquid, with trillium it is a solid. These fluorides have sp3 dehybridization, right? Why so? This we have discussed in chemical bonding. You will say, ma'am, everything you have discussed in chemical bonding. Why? Because these structures are the part of chemical bonding. That's not the part of periodic P block, right? So sp3d, why it exists? Based on the theories we have done, why SF4 has sp3d hybridization and thus having trigonal bipyramidal structure, right? So in which one of the equatorial position is occupied by very, 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 very important. This I told you in chemical bonding as well, that this particular line is a very important line. So what exactly they are telling you? They are saying that you have SF4, right? So they are saying that it is having a trigonal bipyramidal structure. That means this kind of structure it is having. Now the question is, you have only 4F. Where the lone pair will be, right? Where the lone pair will be. So they are saying that which one of the equatorial position occupied by a lone pair. What are the equatorial position? Anybody in the chat box? What is the equatorial position? That I am drawing by this white pen are the equatorial positions. So they are saying that one of the equatorial position will have the lone pair, and this is going to be the structure of SF4. That is why it is called a seesaw geometry. Why? Because if you ignore this thing, it looks like a seesaw only. That is why it is a seesaw geometry, right? Okay, all element except oxygen. Now next one is, all element except oxygen form dichlorides. Now we are talking about di. From tetra we have dichlorides, right? So all element except oxygen form dichlorides like SCl3, SCl2, SeCl2, TeCl2, right? These dihalides are formed by sp3 hybridization, right? They are talking about ECl2, but E should not be oxygen, right? E should not be oxygen, right? So this have tetrahedral structure. They will well known monohalides as well. If you talk about the monohalides, they are well known monohalides as well, dimeric in nature. The well known monohalides are dimeric in nature. They form dimers. Examples are S2F2, example are S2Cl2, S2Br2, Sc2Cl2, Sc2Br2, right? So basically, if you talk about EX, that will exist as a dimer, right? Not as a monomer, right? Okay, so this they are saying that once you react, it will basically give you SeCl4 and selenium here, right? Okay, if you talk about any dimeric halide here, any dimeric halide. Now, preparation is not important for you, right? Preparation is not important for you. Now, we are talking about the dioxygen can be. Okay, now we are going to talk about oxygen here, right? So, for oxygen, some properties are important for you and very few reactions are important for you. So, let us see that by heating oxygen containing salts such as chlorates, nitrates, permanganates, when we heat it in the presence of MnO2, we will get KCl and O2. This is a very, very famous reaction, right? This though we have done like in lower classes as well, this reaction we have done. Thermal decomposition reaction. Do you remember this? We have done in lower classes as well, right? So this is a very like a very famous reaction. So you can just go through this, right? Exclusively, you don't have to study this, right? By the thermal decomposition of the oxides of metal at low temperature, by the thermal decomposition also you can get O2. Then you have this reaction is important, that is from hydrogen peroxide, right? When you have hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide, right? Okay, so that's it about the oxygen. Now let us see the properties. Industrially, dioxygen obtained by air by first removing carbon dioxide. So they are saying that in industries, what we do from the atmosphere only, we remove carbon dioxide, water vapor and other gases. Then the remaining gases are liquefied and fractional distillation will give us dinitrogen and dioxygen, and we will separate these two things by fractional distillation. Right, so basically from air only commercially we use this, right? So now properties is important, right? So let us see some of the properties of oxygen. Dioxygen is colorless, odorless, it is soluble, its solubility in water is to the extent of 3.08, that means it is highly soluble, right? Which is just sufficient for the vital support for marine and aquatic life. Now we know that oxygen, if it is not soluble in water, then what will happen to the aquatic life? It's not possible for them to breathe, right? So they need oxygen dissolved in water. So that's why the oxygen is soluble in water, not to a very high extent, but it is soluble in water so that the marine and the aquatic life can survive, right? It liquefies at 90 K and freezes at 55 Kelvin. Oxygen atom has 3 stable isotopes, this we all know. Molecular oxygen is unique as being paramagnetic. This we have done through MOT also. Why this is paramagnetic? What are the bonding, anti-bonding orbitals involved here? That this thing is important. Why oxygen is paramagnetic? The unpaired electrons are present in which bonding or anti-bonding orbital? This we have done in molecular orbital theory. Right? Very important question this is. In spite of having even number of electrons. Now, dioxygen directly reacts with nearly all metals and non-metals except some of the metals, like you have gold, platinum, right? That's why they are so famous, right? Some noble gases, its combination with other metals is often strongly exothermic, right? We know that when, for example, with carbon we have oxygen, the reaction will give us heat, right? So basically usually it is exothermic in reaction in nature, which helps in sustaining the reaction. However, to initiate the reaction, some external heating is required, as bond dissociation. Enthalpy of oxygen-oxygen bond is very high, that is around 493.4 kilojoule per mole, right? This they can ask you, that the bond dissociation enthalpy is very high. To initiate the reaction, we need something, but after that, it can go on and give us more heat. right? So there are some of the very famous reactions with metals that they have given, how they are giving us different oxides, right? How this reaction is very famous, right? This particular reaction is very famous, right? So you can just see this reaction. Others are the very simple reaction, you can just ignore them as well. Especially they will not ask you these things, right? So in addition to its importance in normal respiration, we know that you guys are bio students, right? You already know that what is the use of, like, how important oxygen is. It's like without oxygen we can't survive, right? Our body, our hemoglobin, that needs oxygen. So it's important to normal respiration and combustion processes. Oxygen is used in oxyacetylene welding. So basically they are talking about welding purposes, right? That you must have seen in some iron making, right? So in welding purposes, oxyacetylene is used in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, right? High altitude flying and in mountaineering, right? So basically where, because of the pressure difference, right, they have difficulty in breathing in high mountains, right? There it is used, right? Then even in the high altitude flyings, right, it is used. In hospitals it is used, right? So the combustion of fuels, for example, hydrogens and liquid oxygen, provides tremendous trust in rocks. Okay, so these are some of the uses, like only some of the uses of oxygen, but actually we can't survive without oxygen. So it is, even if you ignore oxygen, like it has no uses, then how can you survive, right? So next is simple oxides. Now for simple oxides, some oxides, the acidic basic nature here is important, right? Okay, so from where they can ask you the question can be asked on based on simple, based on mixed oxides also, 2-3 mixed oxides also you need to know. Character, acidic basic character of these oxides also, right? Okay, till here any problem? Till here any problem, guys? Any problem till here, right? Right, okay. So let us see. I know if you study these things alone, you will get bored. Right now I am teaching you, that's why you're finding like, okay, ma'am is teaching us, I just need to tick, right? So a binary compound, so simple oxides means these kind of oxides we are talking about, where any metal is combined with the oxygen, that is called simple oxides, right? So a binary compound, oxygen with another element, is called oxide. As already stated, oxygen react with most of the elements, and this is this, okay? So oxides can be simple and there are mixed oxides also. Simple oxides, like when you have the MgO, Al2O3, these are simple oxides. Or mixed oxides. Let us see the examples of mixed oxides, right? In the mixed oxides, this element will be in more than one oxidation state. More than one oxidation state. These are called the mixed oxides, right? So here Pb is in 2 oxidation state. Here iron is in 2 oxidation state. These are called the mixed oxides, right? Simple oxides can be classified on the basis of their acidic. Now this thing is very important. You see and check your previous year questions of NEET from this particular topic. Even if they don't mention anywhere that, okay, acidic, learn acidic, they can ask you acidic basic oxides. They have frequently asked these questions, right? So acidic basic or amphoteric character, and also the neutral oxides, right? This also I have mentioned in, I think, maybe in classification periodicity, I have told you that what are the acidic, basic and neutral oxides, right? I have also made a very interesting short on this. I will again upload that short, right? Okay, so an oxide that combines with water to give an acid termed as acidic oxides, right? Like SO2, Cl2O7, CO2, N2O5, all of these are acidic oxides. For example, SO2 combines with water to give H2SO3, an acid. So these are the examples of acidic oxides that you need to know, right? Very important examples of acidic oxides, okay? acidic oxides. These are the examples of mixed oxides. These are the example of mixed oxides. These are the example of acidic oxides. Then you have, in a general rule, only non-metal oxides are basic oxides. Sorry, are acidic oxides. But oxides of some metal in high oxidation state also have acidic character, and these are Mn2O7, CrO3, V2O5. These are also acidic oxides, right? These are also acidic oxides. These are also acidic oxides. The oxides which give a base are called the basic oxides, right? So what are the basic oxides? Na2O, CaO, BaO. These are the basic oxides, right? So now next is, in general, metallic oxides are basic in nature, right? But now some metallic oxides exhibit dual behavior, that is amphoteric. They show characteristics of both acidic and basic, right? They are called as amphoteric oxide. What are the examples? Like we have Al2O3, example of amphoteric, right? They react with other examples. Let us see the other examples as well, right? Exhibit there, okay, right? There are some oxides which neither acidic. Wait a minute. Here you can also talk about Zn. Zinc oxide is also amphoteric, so you can also talk about that oxide, right? Okay. Yes, they have not mentioned it here. No worries, right? So now, wait a minute. Yes. Next is neutral oxides, right? What are neutral oxides? So the examples of neutral oxides, these are important. Carbon monoxide, NO and N2, right? These are your neutral oxides. Very, very important. Please note down one thing. On some page, on a blank page, write down acidic, basic, neutral and amphoteric oxide. If you want me to make a short on that, then let me know in the comment section as well as in the chat box, right? Okay, yes. Gamers, I have already cleared this up. This thing is important. Some of the pages you can skip, some pages you can't skip, right? Okay, that's why I am here to tell you which page, which reaction you can skip, right? Okay, otherwise they have not mentioned anywhere acidic, basic, but this is a general thing of chemistry you need to know. They will give you that acidic, basic oxides. You have studied inorganic chemistry, you don't know acidic, basic oxides, right? Okay, yes. Now, ozone. Let us talk about ozone. Okay, everybody, let us talk about ozone. Everybody, yes. Ozone is an allotropic form of oxygen, right? It is too reactive to remain for long. Ozone is basically in our not atmosphere, stratosphere, I guess, right? So at the sea level, at the height about 200 kilometers, it is formed from atmospheric oxygen in the presence of sunlight. This ozone layer protects Earth's surface from an excessive concentration of UV radiation, right? UV radiation that is coming from the sun, right? Our Earth is protected now. So I think it was earlier getting depleted, but now it is fixed, right? That depletion is being fixed by the scientists, right? But the kind of pollution that, especially in India, what we are doing, right? What is happening in India, right? So that much pollution, right? So definitely after 10 to 15 years, again, we will see something, right? Okay. Yes. Yeah, the ozone layer is located in the stratosphere, right? So now preparation, you can go through this thing. You need to know one thing about this, that from O2 to O3, that is a endothermic reaction, right? That is a endothermic reaction. It will require some energy, right? Slow dry, this you don't need to know. Then we have, since the formation of this from oxygen is endothermic process, it is necessary to use a silent electrical discharge in its preparation to prevent its decomposition, right? If the concentration of ozone greater than 10% are required, a battery of this all is not important for you, right? Just remember that from O2 to ozone, this is an endothermic reaction, right? Then we have some of the things here, right? Properties. Pure ozone is pale blue gas, right? dark blue liquid, violet black solid. Ozone has characteristic smell and in small concentration it's harmless. If the concentration rises above 100 parts per million in our air, breathing becomes uncomfortable, nausea and headache. Right? Ozone is a thermodynamically unstable. Important point, important line. From here, assertion reasoning questions can be asked. Statement based questions can be asked, right? Ozone is thermodynamically unstable with respect to oxygen, since decomposition into oxygen results in liberation of heat, right? That means that is a exothermic process, right? See, definitely, if we are saying from O2 to O3, it is endothermic. Then from O3, the decomposition to O2, that is a exothermic process. That is a exothermic process, right? Now, next thing is, these two effects reinforce each other, resulting in a large negative Gibbs change energy for the conversion. So, whenever Gibbs energy is negative, that means that process is very spontaneous, right? So, it is not really surprising. Therefore, high concentration of ozone can be dangerously explosive to us, right? So, basically, more the concentration, more the Gibbs free energy negative, spontaneity of this process will increase. That means it will start occurring by itself. That is the reason, right? Okay. Okay. Yes. Due to the ease which it liberates atoms in nascent oxygen. Another important thing is nascent oxygen, that it produces nascent oxygen. That is why it is a good oxidizing agent, right? That is why it is a very powerful oxidizing agent. Right, for example, you have PBS. It is a very good oxidizing agent. It will oxidize it. You have I negative. It will oxidize it to I2. Right, so you can remember that it can oxidize I negative to I2. Right, it can oxidize. This thing is important. I negative to I2. It can oxidize O3. Right, okay. Then reacts when excess of potassium iodide solution is liberate this, okay, liberated, which can be titrated against standard solution, right? So basically these are the titrations, not important. This is also not important for you. You can skip this thing. Another threat to this ozone layer is probably from here the question they will not ask, right? Now the structure of ozone, right? This is the structure of ozone. This is the structure of ozone, very, very important. Right, the structure of ozone, the lone pairs, the resonance involved here, right? The two oxygen-oxygen bond length in the ozone molecules are identical. That means resonance is happening here. That is 128 picometer. The molecules is angular in shape, are expected with a bond angle of about 117. It is resonance hybrid of two main structures. Now its uses, like infinite uses. It is used as germicide, disinfectant for sterilizing water. It is also used in bleaching oils, ivory, flour. These are artificial ozones we are talking about. It acts as oxidizing agents in the manufacture of potassium permanganate. Okay, yes, this we have done. Potassium permanganate in DNF block. Remember in DNF block I told you one reaction of preparation of KMNO4. Remember that reaction or not? Things are interlinked with each other. Remember this reaction of DNF block for the preparation, 3-step preparation. Yes? Now, let us talk about some of the things about sulfur. Now, sulfur is basically rhombus, rhombic and monoclinic, right? So, firstly, to rhombic and monoclinic, it was there when you used to have solid states, right? But now you don't have solid state in your syllabus, right? So that's why just knowing the names and some of the important points is sufficient for you. You don't need to get into the preparation and all of those things, right? So sulfur forms numerous allotropes, of which the yellow rhombic and monoclinic, right, forms are most important, right? So firstly, two forms. First is yellow rhombic, and that is called alpha sulfur. Then you have monoclinic, that is beta sulfur. Forms are most important. The stable form at room temperature is rhombic sulfur, which transform to monoclinic when heated at above 369 Kelvin. 369 Kelvin, right? That means monoclinic transfer. Rhombic is converted to monoclinic, right? Rhombic is converted to monoclinic. Now what about rhombic? This allotrope is yellow in color, melting point is 385.8, right? And specific gravity is this. Rhombic sulfur crystals are formed on evaporating the solution. It is really soluble in, it is readily soluble in CS2, right? Okay, that is important. The melting point is important, right? Then we have monoclinic sulfur. Now here this transition temperature is important for you, right? So let us see what is this transition temperature. So its melting point is 393 Kelvin. Specific gravity is this, it's soluble in CS2. The form of sulfur is prepared by melting rhombic in a dish and cooling, this is it, and it will be formed. Two holes are made in the crust and the remaining liquid poured out. On removing the crust, the colorless needle-shaped crystals of beta sulfur are formed. Basically, till here they are telling you the preparation. Preparation, you just need to remember that monoclinic is formed from rhombic. That's it. Okay, that monoclinic is formed from rhombic, right? Okay, beta is formed from alpha. Then we are saying that it is stable above 369 Kelvin and transforms into alpha below it. Now this thing is important. That is why this temperature becomes very important for you, right? So we know that alpha is converted to beta, and again we are talking about a temperature that is 369 Kelvin. We are saying that if we heat this up to 369 Kelvin, then it will be converted to beta. That means here we have the transition, right? Conversely, alpha sulfur stable below 369 and transforms into beta above this. That means it is 369 where both forms are stable. So this temperature is called the transition temperature, right? So if they ask you the transition temperature, what you need to remember that from alpha to beta, right, when they are interchanging at the particular temperature that is 369 Kelvin, that is called the transition, right? That's it. What you need to remember from here, there are two things, alpha and beta. Alpha is rhombic, beta is monoclinic. Rhombic is converted to monoclinic, that means alpha to beta at 369 Kelvin. That's it. And that is called the transition. That's it, what you need to remember, right? Okay. Okay, guys. Okay. Now, they are saying that both have S8 molecules. These S8 molecules are packed to give different crystal structures. Ring in both the forms is puckered and has a crown shape. The molecules' dimensions are given in this much, right? So now, right, we are having rhombic and the monoclinic, right? So as you can see, this is having a crown shape, right? This is having a crown shape. So rhombic is having a crown shape. This is like a chair, right? This is like a chair, right? This is like a chair structure. This is like a crown structure. That's how they are famous, right? This is alpha, this is beta, right? Okay, alpha and beta. Both rhombic and monoclinic have S8 molecules. The monoclinic dimensions are mentioned here. Several other modifications of sulfur containing this has been done. It's also not important for you. S2 is dominant species and is paramagnetic like O2. Now this thing, wait a minute. In this sulfur, the ring out oxygen. Okay, now this thing is important. At elevated temperature, S2 is a dominant species and is paramagnetic like O2. This thing is important, right? Okay, this thing is important, that when you have elevated temperature, that about 1000 Kelvin, then S2 will become dominant species rather than S8, right? This whole bonds will break and it will become as S2 only, and that S2 is going to be paramagnetic. Otherwise, it exists as crown shape or chair shape, right? Okay, understood everybody? Understood what we need to remember here? Again, I am recapping. See, alpha, beta, two we have. Alpha is rhombic, beta is monoclinic. Alpha is converted to beta, that means rhombic is converted to monoclinic at a temperature called transition temperature, that is 369 Kelvin, Now, other thing what you need to do, that they both exist as S8 molecules. This is your alpha and this is your beta, right? Alpha exists as crown and this exists as chair shape. These are the two shapes in which it exists. Now, when you heat it, the temperature is elevated to 1000 Kelvin. Then the bonds will break and it will be converted to S2 molecule. That S2 molecule is a paramagnetic in nature, right? Okay. Huh. Thank you, Sunil. Thank you. Don't worry. You will get amazing sessions, right, coming up for you next week. See why I am here, so that you can write it down on some page, whatever I'm speaking. That these are the things, these are important points that you need to remember. See, remembering all of these things is not necessary for you, right? Okay, and they have never asked these kind of questions, right? So now let us see sulfur dioxide. This is the preparation of sulfur dioxide, as you can see. This though we all know, right? So now what else is important for you, right? Let us see the properties. Sulfur dioxide is colorless gas having pungent smell and is highly soluble in water. It liquefies at room temperature under pressure 2 atmosphere and boils at 263 Kelvin. Okay, so it is having, first thing is it is having a pungent smell, colorless gas it is, right, and highly soluble in water. That means in water, this is acidic oxide, that is why in water it will form a acid, right? It reacts readily with sodium hydroxide, forming sodium sulfide, this kind, and water. That means definitely this thing is acidic in nature. That is why with the base it is forming a salt and water, right? When it reacts with more sulfur dioxide, now they are saying which then reacts, this then reacts with more sulfur dioxide and give us sodium hydrogen sulfide. Don't need to remember all the reactions, just remember the property that SO2 is acidic in nature. That is why with the base it is giving us salt and water, right? Okay, that is why with base it is giving us salt and water. In its reaction with water and alkalis, the behavior of sulfur is very similar to that of carbon dioxide, right? Sulfur dioxide reacts with chlorine, right? When it reacts, now this is a very, very important reaction, right? These two reactions are very, very important. I'm not saying this with respect to P block. You will see these reactions throughout your chemistry, right? Throughout your NEET chemistry, right? This reaction, right? Now here what you are making? Sulfuryl chloride, right? Sulfuryl chloride, which is a very, very important reagent, right? So now they are saying that sulfur dioxide with chlorine in the presence of charcoal, right, act as a catalyst to give sulfuryl chloride, that is SO2Cl2. It is oxidized to sulfur dioxide. Now they are saying that it is oxidized to sulfur trioxide by oxygen in the presence of vanadium, right? In the presence of V2O5, it is converted to SO3, right? So now they are saying that sulfur dioxide behaves as reducing agent, right? Reducing agent, that means it will oxidize itself. For example, it converts iron 3 positive ions to iron 2 positive ions. Again, it is important, right? And decolorizes acidified potassium permanganate solution. The latter reaction is convenient test for gas, right? Okay, so it also decolorizes acidified potassium permanganate solution, right, which is having 7+ oxidation state. It will decolorize. Here manganese has 7+. It means they are talking about KMnO4. Right, KMnO4, it will decolorize that thing, right? So whenever you see any change in the color, that definitely means that it can be used for the identification, right? Okay, okay guys. Now this is the structure, somewhat similar as ozone only, right? So now this is the two reactions that they have given you, that how it changes Fe3 positive to Fe2 positive, how it changes MnO4 negative, that is KMnO4, to SO42 negative, right? Wait a minute, to Mn2 positive, right? How it decolorizes it. Decolorizes it. Then the molecule is angular, right? Definitely. Now these are the shapes that is given to you. These are the uses. It is used in refining petroleum, sugar, bleaching, wool, silk, anti-chlor, disinfectant, right? Preservative, right? All are the uses of your SO2. Liquid SO2 is used as solvent to dissolve number of organic and inorganic chemicals, right? Okay. Now let us see oxoacids, right? Let us see oxoacids, everybody. Now tell me what can be important with oxoacids. Till now, I think even you have idea. What is very important? That is the structures are very important. Very, very, very important, right? Structures are very, very, very important. So, H2SO3, name is sulfurous acid. This is the structure. Then you have H2SO4, sulfuric acid. This is the structure, right? So, here you had one lone pair. Here instead of that lone pair, you have double bond O. Here this is called, then you have H2S2O8, right? H2S2O8. This is the structure. Everything else is same as this one, right? It's just that this OH and this, if you have one more molecule of H2SO4. For example, you are talking about 2H2SO4, right? What will happen? This is a way to remember things, right? So, this is OH, this is OH, this is double bond O, double bond O, double bond O, this is OH, and this is also OH. Now, what you can do here? Anybody in the chat box, what you can do here? Simply remove water from here, right? And then what you will get? Simply remove water from here, and what you will get? You will get this thing. You will get this thing, right? That is H2S2O 1, 2, 3, 4, 5, 6, 7. Right? So it is same as, so it's not difficult to learn these structures. You just need to understand what is happening here, right? So here it is sulfurous acid. Sulfurous acid, you have one oxygen less as compared to sulfuric acid. Then you have peroxo. Peroxo means you definitely have a, wait a minute, that was this one, right? Pyrosulfuric acid. In the sulfuric acid, when you dehydrate one water, you will have pyrosulfuric acid. Peroxo means you should have a peroxide linkage here. Peroxide linkage means this linkage. So instead of oxygen, you have two oxygens here. That is why this is H2S2O8, right? Okay. This is oleum and a very, very, very important compound, right? This is also used in sulfonation processes. This is used, right? Okay. Any problem here? Any problem here? So these are the four structures and you need to know all the four structures here, right? Then you have, next is manufacture, right? Manufacture sulfuric acid, right? So you need to know that this is from contacts process, right? That this actually manufactured by contact process, which is having which catalyst? The catalyst is vanadium oxide, that is V2O5, where vanadium is in +5 oxidation state, right? This also I have explained you in DNF block, right? What else is important? Absorption of this to give oleum. A flow diagram of manufacture is given to you. The key step in the manufacture of this is catalytic oxidation from SO2 with oxygen to give SO3 in the presence of vanadium. This is the point that you need to remember here, right? What was the catalyst? What is the name of the process? What kind of catalyst and which oxidation state it was used, right? Okay, yes, and that was the overall reaction. And also the important thing is that this is a exothermic process. This thing is also very, very important for you, right? So the reaction is exothermic, reversible, forward leads into a decrease in volume. Low temperature, very important, low temperature and high pressure are favorable. This is according to 𝐂𝐡𝐞𝐤 principle, right? That low temperature and high pressure are favorable here, right? Okay, low temperature, see, high pressure means it will move towards less number of moles. Less number of moles are there in product side, so it will move forward, right? Low temperature, because it is exothermic, so for low temperature it should be forward. This we have discussed in chemical equilibrium 𝐂𝐡𝐞𝐤 principle, right? Are favorable condition for maximum yield. But the temperature should not be very low, otherwise rate of reaction will become very slow. In practice, the plant is operated at pressure 2 bar, this. The SO2 gas formed is converted to absorbed in concentrated this and this. Okay. This they are telling about the sulfuric acid that is obtained is 96 to 98% pure. Not very important. Now let us talk about the properties of sulfuric acid. Right? For preparation, what you need to remember, that what is the all these lines. Vanadium oxide is used, which oxidation state, process name, right? All these things are important. What are the conditions? Low temperature, high pressure, these are the conditions, right? Next is the properties here. If you talk about the properties, regarding these properties, sulfuric acid is colorless, dense, oily liquid with specific gravity. The acid freezes at 283 Kelvin, right? And boils at 611 Kelvin. It dissolves in water with evolution of large quantity of heat. Now, if you have ever seen sulfuric acid, it is very explosive in nature, right? It is very, very explosive in nature. It dissolves in water with the evolution of large quantity of heat, and hence care must be taken while preparing sulfuric acid solution from concentrated acid, right? Now, whenever you are preparing the dilute sulfuric acid, the concentrated must be added slowly into the water while stirring. So, always when you should never add water into the sulfuric acid. Always sulfuric acid should be added to the water. Reason being, it's very, very explosive in nature, right? So the chemical reaction of sulfuric acid as a result of following characteristics. First is low volatility, strong acidic character, strong affinity for water, ability to act as oxidizing agent, very, very important, right? There is also one more thing that you can write here. It is a very good dehydrating agent as well. Very good dehydrating agent, right? And this property has been used, right? In organic chemistry, it has been used, right? That is how the link of organic and organic chemistry is like. Inorganic is actually a base. We learn about reagents, we learn about catalysts, right? So here in aqueous solution, sulfuric acid ionizes in 2 steps. This is your sulfuric acid. Firstly, it is HSO4. Then from that to SO4 2 negative, right? So that though is the dissociation, right? Now this process not important. Next is the large value of Ka. Now important thing, the larger value of Ka1. If you talk about this thing, it is very large, that is it is greater than 1. But here it is 0.001 something, right? So it means 10 raised to power minus 2. Here it is 10 raised to power 1. So that means Ka1 is very large, right? That H2SO4 is largely dissociated into HSO4 and this one. That means if you have 100 molecules, maybe out of that 98 molecules are dissociated, right? Greater the value of dissociation constant, stronger will be the acid. That means H2SO4 is a very good acid, and we know it is one of the strongest acids, right? The acid forms 2 series salts, normal sulfate such as sodium sulfate, and then acid sulfate, that is sodium hydrogen sulfate, right? So different salts it can form. Sulfuric acid, because of low volatility, can be used as manufacturing volatile acids in the corresponding salts. Now, here we are talking about its dehydrating agent quality. Now, it's a very good dehydrating agent. 1 point to note down, important point. Many wet gases can be dried by passing them through sulfuric acid. It's such a good dehydrating agent. It will take out water from everywhere, right? So for example, okay, sulfuric acid, provided the gases do not react with acid. Sulfuric acid removes water from organic compounds. It is evident by its charring action of carbohydrates, right? It will take out water from there and will only produce carbon, right? Okay, we will only be left with carbon here. It is such a good dehydrating agent. Hot concentrated sulfuric acid is moderately, now we are talking about the strong oxidizing power, right? Strong oxidizing agent. So what it will do, in this respect, the intermediate between phosphoric and nitric acid, basically he is saying that it is moderately strong oxidizing agent, right? That means nitric acid is a very good like oxidizing agent, right? So here you have nitric, here you have sulfuric, then you have phosphoric. This kind of pattern it has. Both metals and non-metals are oxidized by concentrated sulfuric acid, which is reduced to SO2 gas. So for example, you have copper, it will be oxidized, right, to CuSO4, and it itself will be reduced to SO2. Again, itself is reduced to SO2. Again, itself is reduced to SO2. Here sulfur is oxidized to SO2 again, and here carbon is oxidized to carbon dioxide, right? Okay, right? Readily undergo reduction. Yes, very good. It will reduce itself to SO2, right? Okay, so these 2 points are important for you. These 2 points are important for you. Even the reactions here are important for you, right? You don't need to mug up the reactions, but you need to understand that if something like this will happen, then H2SO4 will be converted to SO2, right? These are the basic points. Don't mug up the full reaction. Just remember some of the, you don't need to remember this, just an example they have given you, right? Just remember this is a dehydrating agent. This is a good oxidizing agent. Just remember that thing. Next is sulfuric acid. A very important industrial chemical. A nation's industrial strength can be judged by quantity of sulfuric acid it produces and consumes. It is needed for manufacture of hundreds of the compounds and in many industrial processes. See, tell me one thing. In organic chemistry, when we were doing reactions of organic chemistry, like every 5 minutes or every 2 minutes, I use H2SO4. Whether it was a small part of that reaction, right? We used H2SO4 there, right? Acidic hydrolysis, basic hydrolysis, like very basic reactions even used these acids, right? So it is needed for manufacture of hundred of compounds, industrial processes. The bulk of sulfuric acid produced is used in manufacture of fertilizers, right? Other uses are in petroleum refining, manufacture of pigments, paints, dye stuffs, intermediates, detergent industry, metallurgical applications, cleansing metals before enameling. Then you have electroplating, galvanizing, storage batteries in the manufacture of nitrocellulose products, and in the laboratory reagent, right? In your syllabus, you must have used this as storage batteries as well, laboratory reagent. Most of the things so you have seen in your physical chemistry as well as organic chemistry, that how important is H2SO4 in a chemistry world, right? Okay. Okay, guys. Okay, guys. Now tell me, now we are going to start with group number 17, right? Is that clear to everybody? Is there any doubt till here? Now, whatever I am going to teach you is very, very important. Every single line is important. Reason being, now we cannot skip anything, right? So, because we are moving towards the trends now, right? Okay? Okay? And the trends of group number 17 are frequently asked, right? So, Group number 17 means we are talking about halogens. Fluorine, chlorine, bromine, iodine are the main things, right? So let us talk about them. Iodine and astatine. Astatine, we will not even see that. We will only see fluorine, chlorine, bromine, iodine, right? The reason is the halogens are highly reactive, non-metallic, right? Now, now greater similarities. That much similarity is not found in the elements of other groups of the periodic table. Now they are saying that they are very similar to each other. That's why they have a specific name called halogens. There is a regular gradation in their physical and chemical properties. Astatine is a radioactive element, and radioactive elements are not studied, right? Okay, like polonium, we didn't study polonium in the previous lecture, in the previous group, right? That's why we will only study fluorine, chlorine, bromine and iodine. That's it. Okay, understood? Now let us talk about fluorine and chlorine here. Fluorine and chlorine are fairly abundant, while bromine and iodine less. Right now they are saying that fluorine and chlorine, right, they are abundant, but bromine and iodine, they are not very abundant. Fluorine is present mainly in insoluble fluorides like fluorospar, important thing, fluorospar, that is CaF2, cryolide, that is Na3, AlF6, very, very important. Then you have fluoroapatite, that is Ca2PO4 twice CaF2. This is repeated in this chapter, right? And the small quantities are present in soil, river, water, bones, teeth of animals. Sea water contains chlorides, bromides, iodides of sodium, potassium, magnesium, right? Then we have the depositive of dried up seas. They are found in like nature. Certain forms of marine life contain iodine in their systems, right? That is actually fine. There is a study on that, right? Various seaweeds, for example, contain up to 0.5% of iodine, and chili saltpeter contains 0.2% of sodium iodate. So these were all the natural sources where it was found, right? Okay. So if you ask me, do I need to remember all of them? Which are you need to, right? You need to go through them once, 2-3 times, read it, so that if they ask you any statement based question, you can, identify what they are asking you. The important atomic physical properties, let us see that. These are the properties, and properties are very important, right? Okay. So I'm going to write down the trends here. Okay, everybody? Yes, everybody in the chat box. Now, let us firstly see atomic number, easy, atomic mass, easy. Electronic configuration, we know that it will have NS2, NP5 kind of electronic configuration that we can see here. Right, over here we have added 3D also, here 4D also, and here we have added 4F and 5D electrons also. Right, it is same as before. Now, we will not see polonium anywhere. We will talk about fluorine, chlorine, bromine, iodine and the properties here. So if you talk about the first property is the size. First property is the size, very important. Now, as you can see here, the size is increasing, right? So what you can write, fluorine, then you have chlorine, then you have bromine, then you have iodine. Down the group size is increasing, that is clear, right? Then next one is ionization, or you can just simply write ionization enthalpy. Can you see here what is happening? Can you see here what is happening? Anybody in the chat box? Ionization enthalpy, it is decreasing, and decreasing. So you can say that it is decreasing, and decreasing. There is no, but now things are going to be interesting. Now things will get very, very interesting here, right? Okay. Now you can see a very weird trend here. What is that? -333. Then it has increased. Then it has decreased and decreased. Can you see that, anybody? Can you see that? Firstly, it has increased, then decreased, then decreased. That means this is where the question will be asked. Very, very important trend. It has been asked so many times. Check out your previous year question. It has been repeatedly asked, right? So the trend is the trend of electron affinity, electron gain enthalpy, electron gain enthalpy is, you are thinking that it should increase, it should decrease like this. It should be the normal trend. But here, there will be a change over here that you will observe. This is the change that we observed. Can you tell me the reason behind that change? Can anybody tell me the reason behind this change? Why so? Why this happened here? Electron gain enthalpy. To gain the electrons. See, fluorine is the smallest element among this periodic table. It is very, very small. Throughout this periodic table, it is very, like, this is the smallest element of this periodic table, right? So, fluorine has how many lone pairs? 1, 2, 3, 4, 5, 6. If it is forming one bond, it has 3 pairs of lone pairs, right? 1, 2, and 3. So, smaller the size, more will be the electronic repulsions, right? More will be the electronic repulsions. Because of those electronic repulsion, though it should have the capacity, because it is highly electronegative, it should have the capacity to accept the electron, because down the group electronegativity is going to decrease. It should have the capacity to accept the electron. Its electron gain enthalpy should be maximum. But because of these electronic repulsions, its electron gain enthalpy is less than that of chlorine, right? This is reason is due to lone pair repulsions, due to repulsions, you can say, due to repulsions for the incoming electron. Okay, understood why it is so? Everybody in the chat box, are you able to understand this, why this is so or not? Why this is so? Everybody, right? Now, next thing is electronegativity. If you talk about electronegativity, then the answer is going to be, here it is increasing, then it is decreasing, then it is decreasing, right? Okay, wait a minute, it is decreasing only. Yeah. That's what I was thinking. It is decreasing only, no? So yes, it is so simple only. It is decreasing. So it is fluorine, then you have chlorine, then you have bromine, then you have iodine. Nothing like change here. The one that I am drawing by green are same only. If you talk about the hydration, it is also decreasing only. So there is no change here, right? Delta hydration. It will be fluorine, then chlorine, then bromine, then iodine. The question that is asked is from electron gain enthalpy. Okay? Yes. Understood? From this table, we have these 5. Out of this, from here the question will be asked. Next is these points, right? Again, we are going to write down the trends here, right? From trends only we can see. If we see the melting point here, melting point is definitely same. It is increasing, no change here. Fluorine, chlorine, then you have bromine, then you have iodine. Boiling point is also same only. It is increasing. Fluorine, chlorine, bromine, iodine, right? This is also done, this is also done. Density is definitely also increasing, right? Density is also increasing. Why density? See, size is increasing, so density will also increase, right? Okay. Now the important distance, okay. Important question is this one. Bond association enthalpy. This is a very, very important question from where the questions are asked. Now, firstly, this is also increasing, no issues. Distance down the group is obviously increasing because the size is increasing, so distance is also increasing. Simple. Bond dissociation energy. What kind of trend you can see here? Firstly, it decreases, then it increases, then again it decreases, right? So can I say basically here the maximum is for chlorine, then you have bromine, right? Then you have fluorine, then you have iodine. What should be the correct? Firstly, this is the correct. What should be the correct? Right? This is the correct answer. But what should be the correct answer? What we assumed? We assumed that down the group, the length is increasing. So the bond dissociation energy should decrease, ma'am. Because the longer is the length, the more easy to break that bond. Right? So bond dissociation, do you agree with this point? That bond dissociation energy should decrease down the group. Firstly, tell me, do you agree with this or not? Everybody in the chat box, do you agree with this or not? Everybody in the chat box, do you agree with this or not? Right? Okay. So down the group, it should decrease. It should be F2, then it should be Cl2, then it should decrease, yes. F2, then Cl2, then you have Br2, then you have I2. But something here happened to this fluorine. It jumped from this position to this position. Can you see this? Here also something happened to fluorine where it was. Something happened to fluorine. It jumped from the first position to the second position. Right? For example, fluorine is the topper of the class. Right? Now he is on the third position, not on the first position. Something might have happened. What has happened? The reason is same. Right? So what exactly happened? Why? It was supposed to have the maximum bond dissociation enthalpy, but it is less. Can you tell me any reason behind that? It is simple, guys. As I told you before also, this fluorine is very small. It has 3 lone pairs over it. Because of this, these repulsion in these electrons, these lone pair repulsion, they will make it really, really unstable, and that is why it is easy to break the bond of F2 as compared to Cl2 and Br2, right? Because of the electron repulsion. You can say lone pair repulsions, right? It's like someone who is very, very, for example, someone who used to be very poor. Now you give them like millions and millions and billions, but they are not able to handle it. They will go crazy. So fluorine size is very small, but has a lot of money. So he has went crazy. He's like, I don't know what to do with this money. So that is why he is not the winner, but chlorine and bromine becomes the winner. So these two are very, very important and very frequently asked questions, right? Okay. Okay, guys. Now, next is the E0. E0 is definitely decreasing here. So, you can write it decreases. Right? Okay. Okay, guys. Size also you can say directly that it increases. Ionization enthalpy, it decreases. Right? So, you can write down all the things that are increasing and decreasing and the exceptions. These two exceptions, this first exception and this second exception. Right? Okay, that is your work, right? So now next is now all the things that we are going to study here. I've already told you we are just going to read the theory, right? So all the elements, they possess Ns2Np5, right, which is 1 electron short. Now because why it has such a high power to gain the electron? Because he is like, I am at Ns2Np5. If I gain 1 electron, I will become this noble gas configuration. And who, like, do you want to be stable or not? You are like, ma'am, I want to be stable, ma'am. I want to crack NEET. I want to become a doctor. I want to have that financial, emotional independence. I want to have that respect in the society. Is it that? That is why you want, that is why you are here, right? That is why you want to study. If I tell you after cracking NEET, nothing will happen. You will like, then why I would crack NEET? Right? You know that something I will get out of that. That is your motivation. So its motivation to gain one electron is to become noble gas configuration, right? So it also, they also want to be stable. To become stable, they just need one electron. That is why they have a they have -1, because they want to gain one electron here, right? So the halogens have smallest atomic radii in their respective periods. We know that along the period, the size will decrease, and down the group the size will increase, right? So basically what we want to say that halogens will have the smallest size. Now tell me, ma'am, why halogens don't, why not these noble gases? See, noble gases are fully stable. They are very happy, like very happy, khilkhilate, very, very happy in their life. Cheeks are blushing, dancing here and there, right? So they are like, they have more size. That is the reason. Because they are very stable. They don't want any electron, right? So they want one electron. The halogen is the smallest atomic radii in their respective period due to maximum effective charge, maximum effective nuclear charge. The atomic radii of fluorine is like the other element of this second is extremely small. Atomic and ionic radii increase from fluorine to iodine due to increase in atomic number. Down the group, atomic size will increase. They have very high electronegativity. The electronegativity decreases. Fluorine is the most electronegative element of this periodic table and the smallest. It's like chota packet bada dhamaka, right? Have you heard that term, chota packet bada dhamaka? Those who understand Hindi, it's like in a small packet you have a big bomb, right? So it has very small size, but it has a lot of like power to gain the electrons, not to gain the electrons, it's very clever that it wants to have that shared pair of electrons. That is why its electronegativity is 4, right? Maximum. The fluorine is most electronegative element in the periodic table. They have little tendency to lose electron. They don't want to lose electron. They are like, why would I lose electron, bro? Why would I lose electron? I want to gain one electron. What are you doing to me? You give me one electron and make me noble gas. What are you doing? You are like, okay, lose one more electron. You're like, are you crazy or what? What you want me to do? You want me to lose one electron and become NP4. What would I do with that? If I can gain one electron and become NP5, right? So, due to increase in atomic size, ionization enthalpy decreases down the group. Down the group, what will happen, right? Down the group, their size is increasing, right? So their size is increasing. That is why electron is far away from the nucleus. The distance is much larger. You are far away from your parents. Now what you will do? Your friend will call you. Hey, let's go to this party. You will be like, okay, I don't have anyone to ask, right? No permission required. But right now you are in your house, right? So you have to take permission. So halogens have maximum negative electron gain enthalpy. They are like, I am crazy to gain the electron. Like they have maximum tendency, maximum affinity to gain the electron, right? That is why the electron affinity is positive and the electron gain enthalpy is negative here. In the corresponding period, this is due to the fact that because to complete their one electron, they will become noble gas. Electron gain enthalpy of elements will become less negative down the group. Less negative, this whole we have talked about, right? This whole thing we have talked about. However, the negative electron gain enthalpy of fluorine is less than that of chlorine. It is due to the small size of fluorine atom. As a result, there are strong internuclear repulsions in the relatively small 2p orbitals of fluorine. Thus, incoming electron does not experience much attraction. Smaller size, lone pairs, they will repel each other. That is why it will not be able to gain the electron, right? Very important point. This statement, this paragraph is very important, right? This whole paragraph is very important. Mark it important, right? Very important paragraph. Next thing is physical properties, right? Let us talk about the physical properties. Melting point, boiling point that we have discussed. Halogens display smooth variations in their physical properties, right? Fluorine and chlorine are gases, right? Bromine is a reddish brown liquid, right? So iodine is a solid, right? Their melting point, boiling point steadily increase in the atomic number. All halogens are colored. This is due to adsorption of radiation in the visible region, which results in excitation of outer electrons to higher energy level. By absorbing different quanta energy, they display different colors. So basically they are saying that why halogens are colored in nature, right? So this part, assertion reasoning, they can ask you. See, this can be asked in assertion reasoning question. All halogens are colored. Why? Reason is this one. And usually in assertion reasoning, they will pick out exact the lines of NCERT only. They will just copy paste that thing. It is due to adsorption. We know that they will adsorb, right? Then there will be electronic transitions. It will come back. It will give complementary colors. The same thing that they are talking about. This is due to absorption, not adsorption. Absorption of radiation in the visible. Visible, that is visible to my eyes. If they absorb some wavelength or frequency of visible region, they will give the complementary color, which results in the excitation of outer electron to higher energy level. By absorbing different quanta, they display different colors, right? Okay. For example, very important thing, F2 has a yellow color, Cl2 is having greenish yellow color, very, very important. Br2 is having reddish brown color, right? Then you have I2 is having violet color, very important. Fluorine and chlorine react with water. Bromine and iodine are only sparingly soluble in water, but are soluble in various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, hydrocarbons to give colored solutions. On curious anomaly, we notice that table, this is smaller enthalpy of dissociation. Now this, bond dissociation enthalpy, enthalpy of dissociation of fluorine compared to that of chlorine, whereas the bond association enthalpy from chlorine onward show the expected trend, that is this one. Now they are saying fluorine is behaving very weirdly. Fluorine was supposed to have the maximum, but it is not having that. A reason for this anomaly is that relatively large electron-electron repulsion that I told you, right? So it was supposed to show F2, then Cl2, then you have Br2, then you have I2. But it is showing this F2, it is showing Cl2, then you have Br2, then you have F2. It is showing this kind of behavior. Why? Because of electron repulsions, right? F2, whereas they are much closer to each other in case of Cl2, right? Okay, understood? Okay, guys. Everybody in the chat box, is that clear? Is that clear? Everybody, is that clear? Right? Yes? Okay. Now, let us see the chemical properties here. Oxidation states and trends in chemical reactivity. See, group number 17 is very important. That's why I'm teaching very slowly here. You know, when it was about the compounds, I was in a fast speed. The reason I was in such a fast speed was because in that some of the things were important. But here, questions are asked from these things only. Right? That's why I'm teaching slowly here, so that everyone can, have that thing in their mind that, okay, I am in the class, I have learned this thing now only. Right? Okay. So, oxidation states, let us see. All the halogens exhibit -1 oxidation state. You must have seen Cl -1, Br -1. Right? However, chlorine, bromine and iodine exhibit +1, +3, +5 and +7 states as well, right? Fluorine will not exhibit this one because fluorine is so very electronegative. It does not want to be like, I am a very sweet person. No. Fluorine is having 4 electronegativity. Oxidation states also explained below. So let us see that. Now they are saying that this is your general halogen atom. We know that it is having NS2, NP5, right? So when it is having de-excitation, when it is having the electrons is unpairing itself, in the first excited state, one electron will unpair and jump to this one. This is happening. In the second case, this will jump here. So two electrons are jumping here. In the third case, this electron will jump here. So basically here it should be just this thing, right? Just this thing. 1, 2, 3, 4, 5, 6, 7, right? It should be the thing. Now, 7 unpaired electrons accounted for plus 7 oxidation state. 5 unpaired, how many? 1, 2, 3, 4, 5, so it is plus 5 oxidation state. 7 means plus 7 oxidation state. Here it is 3, so it is plus 3 oxidation state. Here, it can lose 1 electron, right, and become plus 1 oxidation state, or high probabilities, it will gain 1 electron and become minus 1 oxidation state. Right? Is this thing clear to everybody? What has happened here? Now, if it is not in the excited state, it has 1 electron unpaired, minus 1 or plus 1, gain or lose 1 electron. Here, 1, 2, 3 unpaired, so it is 3. It is 5 unpaired, so 5 oxidation state. It is having 7 unpaired, so plus 7 oxidation state. That is how you will have all these oxidation states of the halogens. The higher oxidation states, like of fluorine, bromine, iodine, are realized mainly when halogens are combination with small or very highly electron negative chlorine and oxygen atoms. They are saying that the higher oxidation state, like plus 7, is observed, plus 7, plus 5, these are observed when it is with fluorine or with oxygen, right, with very electronegative. For example, interhalogen compounds, that means two halogens are combining, right, in oxides and oxoacids. In oxides and in oxoacids, halogens are combining with the oxygen, right? In interhalogen, if halogen is combining with fluorine, right, so like chlorine, bromine or iodine is combining with fluorine, then it will exist in the higher oxidation state, right? The oxidation state plus 4 and plus 6, now they are saying plus 4 and plus 6, occurs in oxides and oxoacids of chlorine and bromine. They will exist only, not in interhalogen, but only in oxides and oxoacids. Here higher means they are talking about plus 7, right? Plus 4 and plus 6 will exist in oxides and oxoacids. Fluorine atom has no d orbital, we all know that. That is why there is no chance of expanding the octet. No d orbital, and therefore cannot expand its oxygen. Being the most electronegative, it exhibits only minus 1 oxidation state. See, if you want to have plus oxidation state, then you need to have something in front of you which is more electronegative as compared to you, right? So chlorine with the fluorine, it will have plus and it will have minus, because definitely, yeah, with chlorine and fluorine, this is highly negative. This is, as compared to fluorine, it is electropositive, right? So apart, fluorine is the like most electronegative element. That is why it will always have minus oxidation state, that is minus 1, right? All the halogens are highly reactive. They react with metals, non-metals to form halides. The reactivity of the halogen decreases down the group, right? Let us see this. The ready acceptance of electron is the reason for strong oxidizing nature of halogens. I want to accept the electron, right? I want to reduce myself. I want to gain the electron. Then I will reduce, I will oxidize you. Right? So if halogen wants to gain the electron and be in the reduction process, then it will oxidize someone else. So it is a very good oxidizing agent, right? So it's a strong, F2 is the strongest oxidizing agent, right? Strongest oxidizing halogen, you would say, right? And it oxidizes other halides in solution, even the solid phase. For example, F2 you have, this is NEX negative. See, these three reactions are very simple yet important, right? These three reactions are very simple yet very important, right? So here they simply what they are saying, that fluorine can oxidize chlorine, bromine or iodine. That is why here X can be chlorine, bromine or iodine. That is how fluorine is itself getting reduced and it is oxidizing X to X negative to X2. Chlorine can oxidize the one that is below them, that is bromine and iodine. That is why on the X position you have bromine and iodine. Bromine can oxidize the one that is below it, that is iodine. So it is oxidizing only iodine. So basically it is fluorine, chlorine, bromine, iodine. Down the group, the oxidizing power decreases. Right? Okay, this you can conclude from here. Right? Thank you so much, Sukanya. Yes, definitely, guys. Let me see how many likes in the chat box. That's why I don't ask you to like that. And that is the reason you don't even like. I don't ask and then you take me for granted. That's why I get hurt. Right? So don't do that. Right? If I am like not asking again and again, then it's your responsibility to support your teacher who is standing for you, just for you, standing here for last 2 hours, right? Just for you guys, right? Okay? Yes? Now, the decreasing oxidizing ability of the oxygen in aqueous solution down the group is evident from their standard electrode potential, which are dependent on the parameters indicated below, right? So these are the, basically they are telling that how the oxidizing ability is decreasing. So from X2, it is like dissociation, how much just to break the XX bond. Then for it to gain the electron, it will become X negative. Then it wants to be in the aqueous solution. This is hydration, that is X2. The relative oxidizing power. So this is a standard process to calculate the electrode potential, right? So the relative oxidizing power of halogen can further be illustrated by the reaction with water. Fluorine oxidizes with water to oxygen, whereas chlorine and bromine reacts with water to form corresponding hydrohalic and hypohalous acids. So they are saying if you talk about fluorines, it will itself get reduced, right? It will oxidize water to oxygen. Now this is a very, very important thing that we are going to do. Very, very important reactions that we are going to study here. Fluorine will oxidize water to O2, right? So fluorine oxidizes water to oxygen, very important point. But it is such a good oxidizing agent, right? But when we compare chlorine or bromine, it will not be able to oxidize it to oxygen. Rather, it will oxidize it to HX and HOX, that is hydrohalic and hypohalous acids, right? The reaction of iodine with water is non-spontaneous. We have to make it happen, right? So this is I negative. We like, it's not a very spontaneous reaction, right? We have to use some external energy to make it happen, right? So with water, it's not a reaction observed with fluorine, right? So it is like, okay, wait a minute, where it was? Yes, iodine with water is non-spontaneous. In fact, I negative can be oxidized by oxygen. So I negative with oxygen, it can be converted to I2. Now, water is behaving as a good oxidizing agent. Understood? 3 things. F2, what it is doing? F2 is converting water to oxygen. Iodine is such a bad oxidizing agent. It will not oxidize something, it will itself get oxidized, right? So it is oxidizing to I2. Otherwise, it's a non-spontaneous only. If we try, it will behave like this. X2, if it's chlorine or bromine, what they will do? They will convert it into hypohalous and hydrohalous acid, right? Okay. So now, next is anomalous behavior of fluorine, right? Next is anomalous behavior of fluorine. Yes, guys, next is anomalous behavior of fluorine. Everybody. Yes, everybody. Clear? Very good. Now, anomalous behavior of fluorines. Let us see the anomalous behavior of fluorines. Why? Can you tell me the reason? Now that this is our 17th group, right? We have done 13, 14, 15, 16, 17 group. Can you tell me the reason? Array, small size, very electronegative, small, very less electron ionization enthalpy, right? Because of those. Fluorine is anomalous in many properties. For example, ionization, electronegativity, electron potential. Then you have all the higher fluorine than the expected from the trends, right? So also ionic and covalent radii, melting boiling point, enthalpy, bond dissociation, electron gain enthalpy are quite lower than the expected that we have seen. The anomalous behavior of fluorine is due to, first is due to reason, small size, highest electron negativity, very small, but so many responsibilities, right? So highest electronegativity, low FF bond dissociation enthalpy. It's not like it's very happy, I'm very small, my bond length is very small, so it is very difficult to break me. No. Because of the electron repulsions, it has low FF dissociation enthalpy. Non-availability of the d orbitals, right? These are the 4 reasons that definitely they can ask you a statement based question on this, right? Okay. Most of the reactions of fluorine are exothermic, right? Very explosive in nature. That's why when we study organic chemistry, we hardly take, like whenever we are talking about halogen, hydrogen, halide, right? We hardly take HF. Why? Because it's very explosive in nature, right? Due to small and strong bond formation by it with other elements. It forms only one oxoacids while other halogens form a number of oxoacids, right? So that's why very small, so many responsibilities, no friends. Right, hydrogen fluoride is a liquid due to strong hydrogen bonding. Other hydrogen halides are gases. Very important. Hydrogen fluoride is a liquid due to its strong hydrogen bonding. You have HF. And one very interesting thing I'll tell you about HF. Let me see if they have drawn the diagram here. They have not drawn it here. Very interesting thing that I have told you in chemical bonding also, that guys, you know, this HF, this is the covalent bond, this is the hydrogen bond. This is the covalent bond and this is the hydrogen bond. You know, in HF, the covalent bond strength and the hydrogen bond strength is almost same. That is why we are seeing the strongest hydrogen bonding it possesses. That is why this is a liquid while others are gases. Understood? This covalent bond of HF and the hydrogen bond between this F and this H are almost same, and this is very rare. This is only in HF, right? Okay, it is very rare. Okay, guys? Yes, everybody? Very good. Wait a minute. Why can't I see your chats? Yes, now I'm able to see your chats. Reactivity towards hydrogen. Now, what kind of halides it is forming, right? So, first thing is this order. This though it's such we have used it so many times. I think from the first day of chemistry only I have started using this thing, right? Everywhere. Right, because there are so many reactions with HF, HCl, right? So we know that down the group, what you have fluorine, chlorine, bromine, iodine, the size increases. That is why bond length increases. That is why it is easy to break that bond. So if you take about dissociation enthalpy, this bond is very small. Here size increases, bond length increases. That is why this is easy to break. That is why bond energy decreases, right? Okay, they all react with hydrogen to form hydrogen halides. Some of the properties of this are given. The acidic strength, right? Very important. Acidic strength is this one. Why this is the acidic strength? Can anybody tell me? See, down the group bond length increases. What is acidic strength? To lose H positive, right? If bond length is very large, bond dissociation energy required is very less. See, energy required if you two friends are very good friends with each other. If they are very good friends, they are very close to each other, that means the length is very short, right? They are very close to each other. Now to break the bond, it is very difficult. So bond energy is very high. That is why they won't be able to give H positive. If they can't give H positive, so their acidic character is very low, right? If we talk about HI, distance is very large. Distance is large, that means, see, size is large, it means distance is large. That means to break this bond, we require very less energy. So that means H positive can easily be given. That means it is a good proton donator. That means it has good acidic strength. That is why this is the order for acidic strength, right? Okay. Next, let us talk about HF, right? HF, HCl, HBr, HI, right? So melting point here, let's talk about the melting point. It is firstly decreasing, then it is increasing, then it is increasing. Boiling point is also a little bit, it is decreasing, then also it is increasing. So basically, there is gadbad in this HF. Can you tell me the reason? See, down the group we know that the size is increasing, right? Okay, so down the group what should happen, right? The melting point and the boiling point should increase, right? Okay, the melting point and boiling point should increase down the group, right? That means it should be like HF, then you have HCl, then you have HBr, then you have HI, right? Melting and boiling point should increase down the group, right? But now what we saw here, what we observed here, that HF has the maximum boiling point. Instead of this, it is at this size. Reason is the strong hydrogen bonding. Because of that, this is the order of melting and boiling point, right? Okay. So that is the order of melting and boiling point. Minimum is for this, then it is increasing. Maximum is for HF because of the hydrogen bonding. Next we have bond length. Acha, do you all remember na why I am saying that down the group boiling point is increasing? Do you remember that? Everybody, this we have done before only. That more is your molar mass, more will be the boiling point, more is the branching, less will be the boiling point. Do you remember that thing? We have done that in chemical bonding also, in organic chemistry. Whenever we started any chapter, we have done this thing, right? So here, that is the reason that these two are important. Then we have bond length. Bond length is definitely increasing down the group. This we have already done, that it is increasing. Then we have dissociation. Dissociation energy is obviously decreasing down the group. This also we have done, right? And what about pKa? pKa value is also, basically pKa value is opposite of Ka. Acidic strength, we know that acidic strength is this one. So pKa value will be HF, then you have HCl, then you have HBr, then you have HI. The same thing is mentioned here. HF, then HBr, HCl, then HBr, then HI. It is basically decreasing only, right? It is basically decreasing only because it is opposite of acidic strength, right? Okay, is this table clear to everybody? There is a weird behavior of melting and boiling point of HF because of hydrogen bonding. Rest is same, bond length is increasing, dissociation energy is decreasing, that we have done. Acidic strength is also increasing down the group. That is why pKa value is decreasing, right? Okay. Now, next is reactivity towards oxygen. Halogens form mainly oxides with oxygen, but most of them are unstable, right? So it will form oxides, but they are not very stable. Fluorine forms, now these are some of the very important oxides, OF2 and O2F2. Here, why they are important? The oxidation state is very important for oxygen. It is X minus 2 is equals to 0. Here, oxygen is in plus 2 oxidation state, right? Here, oxygen, if you talk about the oxygen here, it is 2X minus 2 is equals to x is equals to 1. So it is in +1 oxidation state. That is why this becomes very important. However, only OF2 is thermally stable, right? OF2 is thermally stable. These oxides are essentially oxygen fluorides because of the high electronegativity of fluorine than oxygen, right? Oxygen fluorides, right? Oxygen is just an element that is linked to the fluorides. Fluoride is the fluorine is the main halogen here. Both are strong fluorinating agents. Now this is very important. What is fluorinating? Acha, what was oxidizing agent? That was giving oxygen. What was reducing agent? That was giving hydrogen, right? Or taking out oxygen. What is fluorinating? Which is giving fluorine, right? So they produce fluorine. O2F2 oxidizes plutonium to PuF6. The reaction is used in removing plutonium as PuF6 from spent nuclear fuel, right? So now chlorine and bromine iodine forms oxidize in which the oxidation state of these halogen range from +1 to +7. We will see these compounds, okay, +1 to +7, how it is ranging, right? So it is not for fluorine they are talking about other things. A combination of kinetic and thermodynamic factors lead to general decrease in the order of thermal stability, right? Stability of oxides formed by halogens, right? So see, fluorine, so definitely it is very explosive, it will not form. So stability is, the order of stability is iodine, then you have chlorine, then you have bromine. This is the order of stability. That is why this becomes very important. The higher oxides of halogens tend to be more stable than the lower one, right? Higher oxides tends to be more stable as compared to the lower one, which has higher oxidation states. Okay? Yes? Yeah, I know that is a little bit boring topic. I know that, I can understand, guys. I know. Okay, so let us see this chlorine and iodine again. The cramming thing has started, right? But these oxides are important. See, chlorine oxides, ClO, Cl2O, ClO2, Cl2O6 and ClO7 all are highly reactive oxidizing agents. They produces nascent oxygen, right? And tend to explode. ClO2 is used as bleaching. This is a very good bleaching agent. Bleaching means when, for example, I want to bleach this hair. So what will happen to my hair? It will lose its black color. So that is bleaching, right? Okay. So the bromine oxides are Br2O, BrO2, BrO3 are the least stable halogen oxides. Usually they can ask you about chlorine oxides, right? So middle row anomaly, right? And exist only at low temperatures. They are very powerful oxidizing agents. Iodine oxides, right, are insoluble solids, right? Iodine oxides are insoluble solids, right? Very good oxidizing agents again, right? And is used in estimation of carbon monoxides, right? Okay. Next is reactivity towards metal. So with metal, how much reactive? See, metal is very highly electropositive. These are highly electronegative. So definitely they have very good bond. Right? One is a very good non-metal, other is a very good metal. Halogens react with metal to form metal halides. For example, bromine reacts with magnesium to form magnesium. Now, the ionic character of the halides, see, decreases in the order. First is MF. Why? Because this is highly electronegative. That is why it is forming highly, see, ionic character will decrease down the group, right? That is why it is highly electronegative. It is forming a good ionic compound. But the ionic character will decrease down the group where M is monovalent metal, right, belonging to group number 1. If a metal exhibits more than one oxidation state, the halides in higher oxidation state will be, very important line, the halides in higher oxidation state will be more covalent than the one in lower oxidation states. any metal that exists in maybe 2-3 oxidation states, you are making a halide from that. The higher oxidation state will be more covalent as compared to the lower oxidation state. For example, SNF, SnCl4, PbCl4, SbCl4, UF6. In all these cases, it is having +4. Wait a minute. This is a very, very important example as well. This is +4, this is +4. I think this question also has been asked. This is +6. This question has been asked somewhere. Are more covalent, then this is +2, this is +2, this is +3, this is +4. It's a very, very important line. Very, very important. This line is very important from here, from this part to this part. The example is very important. Right? Okay, this whole paragraph is important. Right? Okay? Okay, yes. Next is reactivity of halogen towards other reactivity of halogens towards other halogens. Basically, interhalogen compounds. Halogen combines amongst themselves to form a number of compounds. They are called interhalogen compounds, right? So, where X is a larger size halogen and X is smaller size halogen. Now, let us talk about the compounds. So, before talking about compounds, I think we should take a break, right? After the compounds, then we will talk about the group number 18, the few structures, because the half of thing we have done, right? But still we are left with very, very important things, right? So, I think we should take break. Okay, guys? Yes, everybody, and those students who are going to leave this because they are like, okay, ma'am is going to take break. But I always tell you, break doesn't mean I'm going to vanish and someone is going to kidnap me in between. That you can't teach. Go and sleep. This is not going to happen after the break, right? So break means I'll take 10 minutes break, and after that I'll join here. And I want all these students that I can see here live. I want all of you to be here after the break as well, because I know you guys just vanish, right? So don't do that thing, because you are going to miss out something very important, right? See, if you can see here, we are at this point. We are still about to cover. We have completed this much. We are about to complete this much, right? So here you will have noble gases, right? The structures that can be directly asked to you, right? So all those things are also very important. Right? Okay. So now I'm giving you break. Sukanya is very happy that without asking, ma'am is giving us break. Okay. So break will be for 10 minutes. Right? I'll just give you the timer here. Right? I'm going to start the break now only. Okay. So see you all after the break. At around, this is 7:10. Okay. I'll see you at 7:10 p.m. Right? So I'm going to write it here only. Class resume at 7:10 p.m. Let's utilize this Sunday, okay? Hello. Okay, so hi everyone, welcome back to the class. Am I visible? Am I audible to all of you or not? Thank you so much, Dikshi, Pradeep. Yes, bacha, am I visible? Am I audible to all of you or not? Am I visible? Oh my god, so much pollution here outside. So much pollution. Can't even breathe. These days, so it's very difficult to breathe even. And you guys also take care of yourself because it's change of season, and we usually think that okay, what will happen to us? We'll just roam around with our summer clothes only. But yes, okay, so take care of your health also. November, December, Jan, take care of your health. Okay, yes, okay, guys. So, shall I start? Shall I start? Yes. So, now let us talk about chlorine here. Let us talk about chlorine. Chlorine was discovered in 1774 by this we don't have to do, by the action of HCl on MnO2, right? So now this was done by the action of HCl on MnO2, right? And then the preparation method, by heating MnO2 with HCl, we get chlorine here, right? Then by the action of HCl on potassium permanganate, we got chlorine here also. Then manufacture of chlorine. Now, this process you can go through once, that this is called Deccan's process, where with HCl and O2, with the use of, in the presence of CuCl2, you will get Cl2 and water, right? Okay, where ClCl2 is acting as a catalyst. Then what is the electrolysis process? Chlorine is obtained by electrolysis of brine solution. What is brine? That is concentrated NaCl. Right, chlorine is liberated at anode, right? Important, chlorine is liberated at anode. It is obtained as byproduct in many chemical industries as well, right? Okay. Now the properties are that it is a greenish yellow gas, right, with pungent suffocating odor, right? Now, next thing about chlorine is that when it has great affinity for hydrogen, right? So that means it can easily react with hydrogen, right? So with Cl2, it is producing HCl, right? If you have H2S, it can produce, if you have H2S, here also it has hydrogen. So it will combine with this hydrogen to produce HCl. If you have hydrogen in some hydrocarbon as well, it will combine with this hydrocarbon and produce HCl here, right? That means it is hydrogen loving, it has affinity for hydrogen, right? Okay, chlorine reacts with number of metals and non-metals that we have seen here only. With excess of ammonia, right? If you have excess of ammonia, chlorine gives nitrogen and ammonical chloride. Now you have excess of ammonia and you have Cl2. With it, it will give ammonical chloride and nitrogen gas. Right, the cold and diluted chlorine produces mixture of chlorides and hypochlorites. This is cold and diluted, right? It will produce a mixture of chloride and hypochlorites. With here also hot and concentrated, but with hot and concentrated alkalis, it gives chloride and chlorate. So this is basically, if you have cold and diluted base, this is when you have hot and concentrated base, right? So this is producing chlorides and hypochlorites, this is producing chlorides and chlorates, right? Okay. Then dry slaked lime, it gives bleaching powder. This reaction is, so we have done like so many times, right? And if you have studied, like if you have interest in science, you must have studied bleaching reagents and all of those things. So with Ca, with lime water and Cl2, it is producing this bleaching agent, where Cl, nascent Cl, is responsible for the bleaching action, right? So chlorine reactant, right? So this is the bleaching, the composition of bleaching powder. They are telling you that this is the composition of bleaching powder. Chlorine reacts with hydrocarbons, right? We know that these reactions, we know that how they occur, right? With free radical mechanism they occur. Now it's a very important thing that we are saying that with free radical mechanism, there is substitution, right? With hydrocarbons, they will substitute the hydrogen part, right, of that. So it is substituting, it is forming methyl chloride. Then two chlorines are substituted in the second place. You have more Cl2 is added. Chlorine water is standing loss its yellow color due to the formation of HCl and HOCl. That is why that will be very, very harmful for us. Hypochlorous acid so formed gives nascent oxygen, which is responsible for oxidizing and bleaching properties of the chlorine. So basically you have, for example, you have standing chlorine, right? So it will form hypohalous acid also, that is hypochlorous acid. So with this hypochlorous or hypohalous, halous is general term, that is HOX, right? If you have this thing, it will give you nascent oxygen, which is going to be responsible for its oxidizing or bleaching action, right? Now, next is, it oxidizes ferrous to, basically if you have ferrous, it will oxidize it to ferric, right? Sulfite to sulfate. Chlorine oxidizes sulfur dioxide to sulfur trioxide, iodine to iodate, right? In the presence of water, they form sulfuric and iodic acid respectively. So all of these things are important. FeSO4, Na2SO3, SO2 and I2, what it is responsible for. It is a powerful bleaching agent. Bleaching action is due to oxidation because it produces this nascent oxygen, right? Colored substance plus nascent oxygen, it will turn colorless. Okay, understood? So what is the property of chlorine? Again, I am giving you the like overall summary of this thing. Greenish yellow gas, affinity for hydrogen, it has affinity for hydrogen, right? Then with cold and dilute, it is forming NaCl. That means it is forming a mixture of chloride and hypochlorite. But with hot and concentration, it is forming chloride and chlorate, right? Then you have, it is also responsible for bleaching agent, good bleaching agent, because of the oxygen that it is producing, right? So that it can turn color to colorless substances. Then we have seen that it is very good in substitution reaction of hydrocarbons. This we have seen, right? Then we have, just give me a second. Yes. Then we have, it's a powerful bleaching agent. This also we have done. Now, it can oxidize, it's very good oxidizing agent. So, these things are important, that whatever is mentioned to you. Ferrous to ferric, sulfite to sulfate, then you have sulfur dioxide to sulfur trioxide, iodine to iodate, right? These things are important for you, right? Okay. It is used for bleaching, then manufacture of paper and yarn, bleaching agent only, right? In extraction of gold and platinum, it is used. In the manufacture of dyes, drugs, organic compounds, DDTs, in the processes, all these processes in haloalkanes, halorines, we have done this. DDT, chloroforms. In the sterilizing drinking water, preparation of poisonous gases such as phosgene, also responsible for Bhopal gas tragedy. Phosgene was actually responsible, the starting indicator of that, right? So tear gas and mustard gas, right? Tear gas, which can produce tears in your eyes. So it is also a starting thing for that, right? Then you have hydrogen chloride. It's a very good acid, right? Bleaches vegetable organic matter in the presence of moisture. Bleaching effect of chlorine is permanent. Matlab, in this thing, the chlorine is not basically as Cl2, rather in the form of HCl, it is showing the bleaching effect. Glauber prepared in this acid by heating common salt with concentrated ester of 4, right? How it is prepared? With NaCl with concentrated ester of 4. It is a compound of hydrogen and chlorine. Now the preparation with NaCl and H2SO4, it is prepared, right? Then it can be directly passed through the concentrated sulfuric acid. This is the preparation we are talking about. It is colorless, pungent smelling gas, colorless liquid, okay. Then this thing is important, that it's a very good acid. That is why the Ka value is 10 raised to power 7, right? So that means it's a very, very good acid, right? It is aqueous solution. It is called hydrochloric acid, right? High value of this indicates it's a very strong acid, right? So it with ammonia, which is a base, it will give you NH4Cl. Then we have, when 3 parts of concentrated HCl, 1 part of this, basically they are talking about, like, let us see. When 3 parts of HCl and 1 part of HNO3, that is nitric acid, 3:1, it is called aqua regia is formed. Now I told you in yesterday's class that gold and platinum, right, it is very difficult to oxidize these things, right? So with the noble metals like gold and platinum, see why gold and platinum is so expensive, right? You go to the market, see the rates of gold, where they are like going. Why? Simple thing is because it is very difficult. Even the gold of our like ancestors is still as it is. Reason? Because you can't, it is as it is even after 1,000 of years. That is the reason it is expensive, right? So what we need is aqua regia. So in jewelry shops, so aqua regia is very common. Here you have gold, aqua regia, this is aqua regia. Now this is being destroyed. Platinum can also be destroyed here, right? We can dissolve these things. Hydrochloric acid decomposes salts of weaker acids also. Like this is weak acid, weak acid, weak acid. So we can dissolve the salts of weak acids in themselves, right? Okay. Next is, it is used in manufacture of chlorine, NH4Cl, glucose from the starch, right? For extracting glue, since starch, from starch to glucose, the hydrolysis, we have used HCl there. In biomolecules, we have done that. For extracting glue from bones, purifying bone plaque, and in medicine and as a laboratory reagent. Just like H2SO4, it also has so many uses. A lab is not a lab without H2SO4 and HCl, right? Then you have oxoacids of halogen. So if you talk about the oxoacids of halogen, what is important? The structures, right? Okay, the preparation is not important. If you talk about HO, if you talk about fluorine, chlorine, bromine, iodine, fluorine forms hypofluorous acid, right? That is HOF. HOCl does not exist. HOI does not exist. HOBr does not exist. If you talk about, oh, sorry. So sorry about that. Yes. HOF, then you have HOCl, then you have HOBr, then you have HOI, right? So these are generally called hypohalous acid. Hal is the word of any halogen. So if you have fluorine, fluorous, chlorine, chlorous, bromine, bromous, then iodine, iodous, right? So that is the hypohalous acid. If you talk about halous acid, in halous acid, what you will have, not fluorine, not bromine, not iodine, you will only have for chlorine. That is HOCl, just add one more oxygen there, right? If you add 2 oxygen, it will be halic acid. In this case, you will have for chlorine, bromine, and for iodine. If you add one more oxygen, that is halic 7 acid, right? So in this case, basically it is called perhalic acid, right? It is called perhalic acid. So this perhalic acid is having 3, like add one more oxygen, and it is having 3 extra oxygen as compared to the hypohalous acid. Okay, so hypohalous, first you have hypohalous, then you have halous, then you have halic, then you have perhalic. These are the 4. Now hypohalous, all of them. Halous, only chlorine. Halic, only fluorine will not have it. And perhalic also, only fluorine will not have it. So I think abhi to you remember, Okay, I think this chart so you have already learned, right? Okay, this way I think it's very easy to remember this chart only, right? What's the big deal, no? So the structures are important, right? So let us see the structures here. See, if you talk about hypochlorous acid, right? So they have just talked about chlorine here. They have not mentioned all the other structures here because it will be same. Here, if you talk about hypofluorous, just replace this chlorine with fluorine. Hypoiodous, replace this with iodine, right? So that's it. So if you talk about hypochlorous acid, you will have oxygen, one hydrogen and one chlorine. That is hypohalous acid. If you talk about halous acid, here you have added one more oxygen. So it will be double bond O is added here, right? Now, I am adding one more oxygen here. So 2 double bond O is added here, right? 2 double bond oxygen is added here. Rest of the thing is same only. If I am adding one more oxygen, 3 double bond O is added here, right? 3 double bond O is added here. That is hypohalous, then halous, then halic, then perhalic. Okay? Okay, guys? Understood or not? Simple? Right? So you don't even need to remember these. Just remember this one. Then add one oxygen, add two. See, hypohalous, halous acid, halic, perhalic. That's it. Okay? Simple? Was it simple? Yes. Yes, everybody. Next is interhalogen compounds. Now tell me, is that simple or not? Right? It was simple. Interhalogen we have already done, right? When two different halogens they combine with each other, that is called interhalogen compounds, like these, right? Now one should be less electronegative as compared to the other. As the ratio between radii of this and this increases, the number of atoms per molecule also increases. The ratio between the size should be less, right? Thus iodine fluoride should have max, very important thing. They're saying iodine and bromine, the radii ratio, the difference in the radii is very less. So they will have less bromine atoms here. But if you have iodine and fluorine, in this case, the number of fluorine will increase, right? So that is why iodine and fluorine should have maximum 7, like that is IF7, having maximum number of atoms. Understood? Less is the size difference, less will be the atoms. More is the size difference, more will be the atoms. In more high oxidation state, it can exist, right? Okay. Now preparation not required, right? So just go through that equal, if you take Cl2F2, you will have ClF, Cl2F2, you will have ClF3 also. Like you will have equimolar and different. If you have F2 in excess with Br, you will have BrF5, right? If you have Cl in excess with I, you will have ICl3, right? So all these things, preparation is not important, but structures are very important, right? Okay, the structures are very important. These structures are very, very important. Let me see. This table, I'll tell you which thing is important here, the formula and wherever the structure is mentioned, right? Okay, so now let us see. Here ClF colored, this is pale brown, detected spectroscopically gas, red ruby, red solid, right? I'll tell you which are frequently asked questions to you, right? Black solid, this colorless yellow, this they can ask you. IF3, yellow powder, BrF3, yellowish green powder. The shapes are bent T shapes, right? They will have this kind of shape, bent T shape, right? Bent T shape, this kind of shape. One, other. This kind of shape, and the bent T matlab the other should be slightly here because of the lone pair over here, because of lone pair repulsions, right? So the shapes are important. Then you have the shape of this one is the most important. It is a colorless gas having pentagonal bipyramidal shape. Very, very important. Pentagonal bipyramidal. That means let's have a pentagon here. A pentagon is like this, no? Pentagon is like this, right? So in a pentagon, you have your all atoms, right? Here you have iodine, you have fluorine all over here. 1, 2, 3, 4, 5. This is in one plane, right? This is a very, very important thing, okay? So here, 2 fluorine atoms, they are like upwards and downwards, right? So pentagonal bipyramidal, right? It's like this, right? Got it? Pentagonal bipyramidal. It's a very, very important structure, right? Then all these structures, IF5, this exists as square pyramidal. How come it is existing as square pyramidal? You have I here, right? 1, 2, 3, 4 fluorines here. Beta, these structures are very important, okay? They have been asked in your syllabus, in your NEET exam, fluorine, right? Okay, so square pyramidal is the structure, right? It's a square here and then you have a upper pyramid over here, right? Okay. Are you able to understand this, or do you want to see the structure? Or that is in your head only, that ma'am, what you're talking? Hanji students, do you want me to make the structures, or that is in your head? Or will you be able to like, yes ma'am, we know that? Some of the structures I don't have currently. Chalo. Next is BRF3. Again, it is square pyramidal, just like this. And CLF5 is also square pyramidal, right? So all these structures, very important. This structure, very important. These structures, very important, right? All these structures are very, very important for you, right? Okay, directly they can ask you. Next is some of the properties here, right? They are all covalent molecules and are diamagnetic in nature. All the interhalogen compounds are diamagnetic in nature. They have unpaired electrons. They are volatile solids, liquids, except CLF, which is a gas, right? All the interhalogen compounds are solids or liquids, but CLF is a gas. Their physical properties are intermediate between those of constituent halogens, except that their melting boiling points are little higher than the expected. Their chemical reactions can be compared with individual halogens. In general, interhalogen compounds are more reactive, right, than halogen, except for fluorine. That means first you will have fluorine, then interhalogen, reactivity I am telling, then chlorine, then you will have bromine. This is the reactivity. This is the reactivity, right? This is because XX bond length interhalogen is weaker than XX bond length in halogens, right? So if you talk about the fluorine, it is having like it easily can react, it is very explosive. Then you have interhalogen, then you have this, and then you have this, and also there was iodine also here, right? Iodine also. But here they are saying that it's reactivity. It is because of the bond lengths, right? Interhalogen compound, the bond length is not very strong as compared to XX, as compared to fluorine, right? All these undergo hydrolysis, giving halide ion derived from smaller halogen, and a hypohalide or halite or halate and perhalate ion derived from larger ion. For example, you have ICl3. Now, which is larger? I. So, I will form either hypohalate or halate or halate, or halite or halate or perhalate. But the smaller one, because chlorine is smaller here, it will form the halogen, So it is important that smaller will form the halogen and the larger atom will form any of this: hypohalite, halite, perhalate or halate. Any of these it can form, right? Okay. Okay. Yes. Their molecular structures are very interesting, which can be explained on the basis of Vesper theory. This molecular structure table also I have shown you. The explanation is there in the chemical bonding. The compounds have bent T shape. Excess compounds have square pyramidal shape. This compound is pentagonal bipyramidal, and they are very important. Usually, if you ask me, from here, the question will rarely be asked. They can ask you diamagnetic character. They can ask you CF. CLF is a gas. Then they can ask you the shapes. This is the most predictable part that they can ask you, right? Then these compounds can be used as a non-aqueous solvents. Interhalogen compounds are very useful fluorinating agents, right? So for example, you have this interhalogen, you want to add fluorine here. So fluorine can be added to this uranium, right? So are used for production of UF6 in enrichment of uranium, right? Fluorinating means which will give fluorine there. That is fluorinating. Okay. So now we are at group number 18. Group number 18. It's the smallest group of your P block. Okay. Let us see. Red, green. Yes. Hanji, everybody. Let us see. Group number 18. So everybody spam group number 18 in the chat box. Spam group number 18 in the chat box. We are about to end this chapter, right? So I want all of you to spam group number 18 in the chat box, right? Okay. Yes, very good. Last topic, last group. Topic, I won't say last group. And it's a very small group, right? You don't have so many compounds. You just need to understand some structures. And trends are also not very different trends you will see. Normal trends you will see here, right? So these are the sant. These are the monks, right? These are the monks of our periodic table. They are like, I don't care about anyone. They are like, I am very happy. Whatever is happening in others' life, I am very happy, very relaxed. So these are the noble gases. They have fully, their electronic configuration is fully complete, NS2, NP6. They are very happy in their life. No gain of electron, no loss of electron. They are like, why to do all these things, right? So now 18 has 6 elements, Hina, Nina or Katrina, right? Xenon and krypton. Then you have radon. These are the 6 elements: helium, neon, argon, krypton, xenon, radon, right? So now Hina, Nina or Katrina, this you can just remember anything here. I totally forgot. This I remember by xenon and radon only, right? So here 6 elements you have, right? Xenon and radon. All these are gases, chemically unreactive. They are very monks. They behave like monks. They have very few compounds because they are termed as noble gases. So happiness is that they have very few compounds only, and from those compounds only they will ask you the question, right? So the first thing is that all noble gases except radon occur in atmosphere, right? So all other gases we have in our atmosphere. Their atmospheric abundance in dry air is 1% by volume. They are very inert. They don't react with anything, of which argon is major constituent. Helium and sometimes neon are found in minerals of radioactive origin, right? The main commercial source of helium in natural gas, right? That is our natural gas. Xenon and radon are rarest element in the group. That is why we will not hardly study about them, but xenon will have some compounds. Radon is obtained as decay product of radon, right? Okay, as a decay we will have radium. As a decay of radium, you will have radon, right? So now important thing is to just see that what are the trends here that it is following. Atomic number, atomic mass, done, right? Now you can see the configuration is fully filled, right? Very happy in their own life, right? Fully filled configuration they have, happy, octet is completed everywhere, right? So no tension. Atomic radius, if you talk about, it is increasing down the group, right? Because number of shells are increasing here. Ionization enthalpy, they don't have very good ionization enthalpy as compared to others. As you can see, it is not a very good ionization enthalpy. They don't want to lose the electrons, right? But if you still that I wanted to lose the electrons, then definitely as the size is increasing, more is the size, less is the ionization enthalpy. So that is why it will decrease down the group. Always IE is inversely proportional to the size, if there is no exception involved, right? Okay. Yes, we'll definitely do a lecture on that. Okay, we'll definitely do a lecture on that. Then you have electron gain enthalpy. So electron gain enthalpy, as you can see here, it is very positive. Why electron gain enthalpy is positive? Because it does not want to gain the electron. It is like, I don't want to gain the electron. I'm already very stable. Why you want me to gain the electron? So that is why electron gain enthalpy is positive here, right? So as you can see here, next one is density. Density is again not important. It is increasing only, right? Melting point, again it is increasing. Boiling point, again not an exception that you can see. Atmospheric content is also not important for you. Okay? Yes, everybody? Just give me a second. Okay? Now, next is, let's talk about this thing here. All noble gases have general electronic configuration, but helium is having a duplet. Many of the properties of noble gases include their inactive nature, as ascribed to the closed shell structures. They have fully filled octets. Due to the stable configuration, the gases exhibit very high ionization enthalpy, right? Why? Because they don't want to gain the electron. I'm so sorry. I think I said low ionization enthalpy. Yes, ionization enthalpy will be very high because they don't want to lose the electron, right? They are fully filled. So why would they lose the electron? Why would they gain the electron? So that will be very high, right? Ionization enthalpy, however, it decreases down the group with increase in the atomic size. Atomic radii increases down the group with increase in atomic number. This also we have seen. Same trend they are following. Since noble gases have stable electronic configuration, they have no tendency to accept the electron, therefore have large positive values, right? They have positive values. They don't want to accept it. I told you electron affinity is how much hunger I have, right? And electron gain enthalpy is how much I have eaten, right? So basically the signs will be opposite. If I don't want to, I'm like, I don't want to eat anything, right? I have negative electron affinity. I don't have hunger to eat this food, right? But you are forcefully giving me that you have to eat it. You are my guest. You have to eat it. I'm like, I'm not hungry. Why are you forcing me to eat something? Like, no, ma'am, you have to eat it. Then I will have, like, my affinity towards that food is not that much. My affinity is negative. That is why I am not able to eat that food. That is why electron gain enthalpy. To gain that electron, I will be very, like, positive, means I will be fully, my tummy is full. That is why it is positive. So sign is opposite to each other, right? So don't see that, okay, negative means less and positive means more, right? That's why I'm again and again telling you, right? Okay. Physical properties. All the noble gases are monatomic, right? H2, not monatomic means like H2 is hydrogen, right? It is diatomic. Helium, H2, this does not exist. Lithium, so it does not exist only. H2O does not exist. Neon 2 does not exist. What is the reason behind that? Because they can't combine, they are very inert. They are colorless, odorless, and tasteless. They are sparingly soluble in water. They have very low melting and boiling point because of the one type of interatomic interaction, that is weak van der Waal interactions. So because these helium, these noble gases, they are not reactive. That is why with each other they will have that van der Waal interactions only, very weak interactions they will have, right? So it has unusual property of diffusing through most commonly used laboratory material such as rubber, gas, plastics, right? Then you have chemical properties. The noble gases except helium have completely filled electronic configuration. It also has complete filled duplet. They have high ionization enthalpy and more positive electron gain enthalpy, right? They don't want to gain the electron. They don't want to lose the electron. They are very happy, right? So this thing is very important. This question also has been asked. This is very important, and this question also has been asked to you so many times, and students usually mark it wrong, right? So it has high ionization enthalpy, but more positive electron. Students will be confusing electron gain enthalpy only. No ma'am, it should be negative, it does not want to gain. Array, negative means it wants to gain the electron, okay? Understood? Now, the reactivity. The reactivity of noble gases have been investigated occasionally ever since their discovery, but all attempts to force them to react. Now this paragraph is important, huh? Why? Because now they are suddenly saying that there should be compounds of noble gases. How they can exist? They are so unreactive. So, but all attempts to force them to react to form compounds were unsuccessful for a quite few years, right? In March, Neil Bartlett, right, he was like, okay, I have to do something. Then at the University of British Columbia, observed the reaction of noble gas. He was like, I will react them. It's somebody who don't want to get married, you're forcefully auntie saying, okay, I have a girl for you, I have a boy for you. They're like, I don't want to get married, no. Like, no, I have a girl for you, I have a boy for you, right? Typical Indian society, right? So here, now what they're doing, first he prepared the red compound, right? Firstly, he prepared a red compound which formulated as O2 PtF6 negative. You will say, ma'am, here you don't have any noble gas. Wait a minute. Now he is saying that helium then realized that, wait a minute, helium then, he then realized that the first ionization enthalpy of molecular, now this is important, very, 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 very important line, right? He will replace this O2 with xenon. Why? What is the reason? The reason is he then realized that the first ionization enthalpy of molecular oxygen was almost identical with the xenon. This is the assertion reasoning question can be asked. The first ionization enthalpy of the molecular oxygen O2 was same as xenon. So that is why he replaced this with xenon. He said that means if the ionization enthalpy is same, if I replace it with xenon, this compound can be prepared, right? So he made efforts to prepare same type of compound with xenon and was successful in preparing this, right? By mixing PtF6 and xenon, he prepared this compound, right? After this discovery, a number of xenon compounds, mainly with most electronegative elements like fluorine and oxygen, have been synthesized. Okay? Yes. Thank you so much, Sukanya. Thank you so much, Bacha. Now we have this thing. The compounds of krypton are fewer. Krypton, xenon only you will see maximum. Only the difluorides has been studied in detail. Compounds of radon have not been isolated, but only identified. They have not been studied by radio tracker because it is a radioactive technique. No true compounds of argon, neon or helium are known yet, right? So that's the reason we will study xenon compounds. The structures of these compounds are very important for you. Okay, understood? Radon, you have one compound that we will not study in detail. Krypton has one compound that has been studied but not in your syllabus. Xenon has compound. Helium, neon and argon does not have any compound. Right? Okay. No, previous year questions are not there actually today, but don't worry, I'll pick out previous year. I will take a separate session for previous year question of P block. Okay. Otherwise, the lecture would have been really long. Right? Okay. Xenon fluorine compounds, right? Xenon forms the binary fluorides. Now, I'll have one thing for you. I'll tell you in the end. Okay? I'll tell you in the end. I'll have one thing for you from where you can, this problem will be sorted. Xenon forms 3 binary fluorides, that is ZeF2, Ze I'm saying, XeF2, XeF4 and XeF6, and these structures are very important. You will see that. Check out the previous year question, you will see the structures. By the direct reaction of element under appropriate experimental conditions. How it is prepared is not important for you, right? But the structures are very important. The properties are important. Can also be prepared this and this. Are colorless crystalline solids and sublime readily. They are powerful fluorinating agents, again because they are giving us fluorine. They are readily hydrolyzed even by traces of water. It will be hydrolyzed to give us xenon. The structures of 3 xenon fluorides can be deducted from VSEPR and are shown in figure. This will see what are the structures, right? Very important. First is XeF2. Then you have XeF4. Then there is the third one is, this is XeF6, right? Then you have XeOF4, very important. XeO4, very important structure. All these structures are important for you. Anything can be asked to you, right? These are based on the VSEPR theory we have done in chemical bonding. I have taught you there also. If you remember, I have taught you these things. Do you remember? I forgot, ma'am. It's long back, ma'am. It vanished out of your head. Huh? So this is XeF2 that existing in a linear shape. Why? Shape means lone pairs you will not consider here. Right? Lone pairs, hide the lone pairs, you will have a linear shape here. Right? If you talk about the square planar, because it is forming a square here, right? And there is no other bond pair existing. These lone pairs you will ignore, right? Here it is existing as which thing? This is existing as distorted octahedral, because in octahedral it's like this. This is octahedral. You have one more lone pair. Because of this, there will be lone pair, bond pair repulsions. Hence, it is distorted octahedral, right? Okay. Then you have square pyramidal. You are forming a square here and one pyramid, and this pyramid is going to form a pyramid over here. With this thing, it is going to form a pyramid. So it is square pyramidal. What about this one? Hide this lone pair, you will have a pyramid over here, right? This is a pyramid, right? This is the formation of a pyramid, like this kind of pyramid will be formed here. So that is why it is called pyramidal. Those who are not able to understand these shapes, go through my lecture of chemical bonding in detail with these molecules, these kind of molecules, right? I have shown you in 3D what exactly these shapes looks like, okay? Yes, okay, yes everybody. Now let us see the structures we have seen, right? Linear and square planar, this all we have seen, that what is the structures and all of that. Xenon fluorides react with fluorine, fluoride ion acceptors to form cationic species and fluoride ion donors to form fluoroanions. That means if it is giving it fluorine or it is losing fluorine, right? So if it is reacting with fluoride ion acceptor, it will give the fluorine, it will become XeF positive. If it is taking the fluorine, it will become XeF7, right? It depends on what is the reaction that is happening, right? Last one is uses. Helium is non-inflammable light gas. If you talk about helium, that is helium, so we even use that in like balloons. Have you seen that a funny, like fun game where you have helium like helium balloon, they ask you to inhale it. It's not a very good idea though, right? So you inhale it and your voice will change. Have you seen that? Have you seen that? I think with the Kapil Sharma show, I have seen that, like in so many other fun games also. Very fun game to play, but again, inhaling a gas like this is like, it's not like bad for your health. Obviously, it is in the environment, but why to do that, right? Why to do that? So helium is non-inflammable. Now, do you know why it is used in balloons? Why hydrogen is not used in balloons, right? Because hydrogen is flammable, right? So balloons, it can carry that fire, right? So it will explode. So for that, helium balloons are used, right? Even now, the people don't use that, but yes, helium balloons, helium is inert in nature. That is why it is used. And light gas. Hence, it is used in fillings balloons for meteorological observations. It is used in gas-cooled nuclear reactors. Liquid helium finds in cryogenic agent for carrying out various experiments at low temperature. Because it is inert, it can stay for that time. It is used to produce and sustain powerful superconducting magnets, which essential part of modern NMR spectroscopy. Now, NMR spectroscopy, that you don't have, is one of my favorite topics from my master's, like for my bachelor's as well as master's. Yes, this is the one topic, NMR spectroscopy. The reason I am a chemistry teacher, this thing is a reason. So when I went to graduation, I was like, okay, chemistry. I was confused. I was always confused whether to choose maths or chemistry, right? Where should I go? Chemistry or maths? Because I liked both of them. I was like, what to do? Let's see in graduation. Maths, I find it really boring in graduation. I was like, what I am doing here? Like, I am just cramming the theories and theories. And chemistry, I used to find it interesting. But when I saw this NMR spectroscopy, in that, what we used to do, we used to predict that which is that compound by like lot of hints. It was like a quiz. Like, so we used to sit there in extra classes on a corridor, right? We used to think that, okay, this is alcohol, this is maybe ketone, maybe this compound, maybe that compound. So it was a very interesting process, right? So thank God I had a very excellent teacher of organic chemistry. And because of him only, I was like, I have to do masters in chemistry only. Because if this is chemistry, because that topic was newly introduced in graduation. Other things were like similar that I have learned before also in 11th and 12th. But this NMR was something like out of the world. I was like, okay, now my brain has like completely opened up to understand what exactly this is. So it was like really, really interesting. Then we have MRI for clinical diagnosis. It is used in as a diluent, diluent for oxygen in modern diving apparatus. So you know what is this? This we have studied in solubility as well. That helium is added. Scuba divers, they add helium. Why? To avoid bends, because when you go down in the sea, right? In the sea, so what will happen when you like scuba divers? We went into the sea. What will happen? Na? The solubility will increase, right? After they come out, the solubility will decrease. Because of that process, there will be bends. So to avoid that, they need a gas in that gas chamber which is totally inert. So that is why helium is added there, right? So neon is used in a discharge tubes and fluorescent bulbs. For this, so we know that neon bulbs, it is famous by neon bulbs, right? So it is very famous by, my middle NCERT question are there now. So taking a NEET exam, ma'am. My middle NCERT questions are there na, that one also asking a NEET exam. Yes, you can go through that. Everything that I have mentioned here, yes. You must go through the exemplar and NCERT questions. That is a must. Argon is used mainly in provide inert atmosphere in high temperature metallurgical processes where you need inert atmosphere for filling electrical bulbs. It is also used in laboratory for handling substances that are air sensitive. No significant use. There is no significant use of xenon and krypton. They are used in light bulb designed for special purposes, right? So neon you know, argon you know, so that is the basic use of neon and argon. Okay, yes everybody. So we have finally completed the chapter P block from your 11th as well as 12th class. Yes. So now one of the students was asking that, ma'am, previous year questions. So let me give you some previous year questions from here only, right? So let us see, wait a minute. Let us see your previous year questions here. So I don't know if you're able to see this or not. Let me, okay, I think now you will be able to see this. So now, let us see the previous, and you guys have not liked the session, is it? Yes, ma'am. We are very bad, ma'am. We won't like this session, ma'am. Now, as you can see from here, from this side, this is Get Complete NEET Preparation Treasure Box, okay? You just need to click here and you will get to this portal where you will have chemistry, physics, bio, all the sections you have. But I'm specifying the chemistry section here. So in the chemistry section, what you will have, let me show you. If you want to do P block, right? So let me see the P block questions, right? Hyperconjugation, isomerism, if it is, this is, wait a minute, exceptions in organic chemistry, right? So these are your previous year questions. I think it is yet to be uploaded. Yeah, it is not uploaded yet, right? But I'll ask the team to upload it, right? Okay. Okay, here it is, P block. Yes, I was just looking for that. So this is your P block. You just go through this one, P block elements, right? Class 12th, and go through this. This is your previous year question test. Click on this, right? Then what you need to do, then you need to fill your number or email ID. After this, start giving the test. It will be 10 questions, right? So now only we have done P block. So I would advise you to give the test today itself. How many of you promise me to give the test today itself? Guys, I am giving you the homework and I want all of you to give the test, okay? That's your duty now. That's your duty now, okay? That's your duty now. So next one is those students who are, because we have completed our syllabus and now we have these flashcards, as I can show you. Wait a second. So these are our flashcards. Bacha, thank you so much that you were here, but I would only appreciate that thing if you guys also give the test, right? That is totally free of cost. I want you guys to give the test of P block, okay? That's a promise. Give me that promise, everybody. Give me that promise, okay? Now, guys, as we have completed the syllabus, now we are going to start the revision. Practical chemistry I'll do after 20-25 days so that we can also do the revision side by side. Right now, for revision, we have these flashcards for you, as you can see, and these are really, really amazing, really amazing. I am a teacher myself. If I tell that, ma'am, if you were a student or you are a teacher, right, ma'am, would you like these flashcards or not? Guys, I totally love these flashcards, you know, these are my favorite things, right? Why? Because not only these flashcards, along with this, you will get this booklet also, where all the naming reaction are given in a very concise manner, in a very to the point manner. Naming reaction, distinguished test, important points, important examples. Full organic chemistry is mentioned here. And here you have the flashcards of physical as well as inorganic chemistry. You will get this kind of box for it. And same kind of things will be provided to you for bio as well as physics, right? So what you need to do, you just need to go here, right? And here winter sale is going on. Now, just click on the buy now option, right? And then you will get to this portal, right? And here it is at total amount is 1320. For now, it is 1320, right? This is going on currently. My duty is to tell you that this thing is going on currently. So what you need to do, right? You just need to click on this cash free payment. See, cash on delivery is not applicable now. You can use any option here, right? any option, Paytm, you can use any other bank also, you can use like cards, wallets, net banking, anything you can do. Right after that, just pay now, right? Fill everything and that's it. It will be shipped to your house. Give your like shipping address here, it will be shipped to your house. Okay, yes. So that's all for today, and then bye bye, take care, see you all. And I really hope that you will do the previous year question test and this flashcard also. Purchase it as soon as possible. Okay. Okay then, bye bye, take care, see you all in the next lecture where we are going to do, that is going to be a surprise for you, right? So you can see that in the live sessions only, we are going to start the revision. Okay, bye bye, take care.